What if the foundations of modern science began not with a machine, but with a man who dared to question ancient truths, who timed swinging lamps by eye, and who turned a simple telescope toward the sky, only to discover a universe far stranger than anyone imagined? This is the story of Galileo Galilei, mathematician, physicist, astronomer, and the father of modern science. In the next 3 hours, we'll trace how his observations, experiments, and bold ideas reshaped the world forever. No noise, no rush, just slow, thoughtful science, explained clearly, piece by piece, ideal for learning or for drifting off. Before we begin, let us know, where are you listening from and what time is it right now? Scroll down, drop it in the comments. We're building a global constellation of minds, united by curiosity. Now, let's begin. Before Galileo Galilei changed the course of scientific history, the word science didn't mean what it means today. It was not a method, not a process of observation and testing. Instead, science was still deeply rooted in natural philosophy, a branch of thought that tried to understand the world through logic, deduction, and inherited authority, especially that of Aristotle. For nearly 2,000 years, the dominant understanding of the natural world came from the works of Aristotle, a Greek philosopher who lived in the 4th century before the Common Era. His ideas were not tested in the modern sense. They were reasoned through syllogisms and supported by occasional observations, but not subjected to systematic experimentation. Aristotle believed, for example, that heavier objects fall faster than lighter ones. He claimed that the speed of falling was proportional to weight. In his worldview, a rock weighing 10 units would fall 10 times faster than a feather weighing 1. This idea seemed intuitive, and for centuries no one felt the need to question it. In Aristotle's physics, motion was caused by a natural place and a natural state. Earthly objects had a natural tendency to move toward the center of the universe, which was thought to be the center of the Earth. Fire, on the other hand, moved upward by nature. If an object was at rest, it was considered to be in its natural state. If it was in motion, something had to be actively pushing it. And if that pushing force stopped, Aristotle said the object would immediately stop too. The idea of inertia, or continuous motion without continuous force, simply did not exist. Above the Earth, the heavens followed entirely different rules. According to Aristotle and his follower Ptolemy, the sky was made of a perfect substance called aether. This celestial material did not decay, did not change, and moved in perfect circles. This idea was formalized in the Ptolemaic system, where the Earth sat motionless at the center of the universe, and all celestial bodies, planets, the sun, and even the stars moved around it in complex loops called epicycles. These circular orbits were stacked within each other to account for the strange, sometimes backward paths planets appeared to take in the sky. This Earth-centered system was elegant in its own way, and it was mathematically precise enough to predict celestial events with fair accuracy. That made it incredibly persuasive, especially because it also aligned with the teachings of the Catholic Church, which emphasized humanity's special place in the cosmos. The Church didn't merely tolerate Aristotelian physics, it embraced it, because if Earth was the center of the universe, and humanity lived at its heart, it fit the religious narrative that humans were created in the image of God and held dominion over creation. To challenge this framework was not simply a matter of science, it was a challenge to philosophy, religion, and social order. That was the intellectual atmosphere into which Galileo Galilei was born in the year 1564. For generations, knowledge had been preserved and transmitted through authority. If Aristotle said it, and the Church accepted it, then it was considered true. Observation might be used to illustrate a point, but it was not a tool for testing or falsifying it. There was no structured method for empirical investigation. In modern science, we expect ideas to be tested, measured, and subjected to peer review. But before Galileo, this was not the norm. The concept of a scientific method had not yet been developed. There were no controlled experiments, no system of error margins, no standard instruments for measurement. Universities focused on logic, metaphysics, and theology. Mathematics was treated as a tool for calculation, not as a language for expressing physical laws. Nature was something to be understood, philosophically, not interrogated experimentally. But some changes were already in motion. In the early 1500s, Nicolaus Copernicus, a Polish astronomer and mathematician, proposed a revolutionary idea that the Earth was not the center of the universe. Instead, the Earth orbited the Sun. This heliocentric model placed the Sun at the center, with Earth and the other planets revolving around it, At first, the Copernican model was treated as a mathematical convenience, not a physical reality. It made calculations easier, but few believed it represented the true structure of the cosmos. After all, the model violated common sense. If the Earth was rotating, why didn't people feel it? If the Earth was moving through space, why weren't birds and clouds left behind? And there was another problem: parallax. If Earth really orbited the Sun, then stars should appear to shift in position throughout the year. This shift, known as stellar parallax, could not be observed with the naked eye, so many took its absence as evidence that Earth was stationary. Copernicus had planted a seed, but that seed would need someone like Galileo to grow, someone who would observe, measure, and demand physical evidence. Someone who would replace appeals to authority with empirical proof. Someone who would build instruments, conduct experiments, and write clearly enough that his ideas could not be ignored. Galileo would not accept Aristotle's word on motion. He would not accept Ptolemy's model of the heavens, and he would not accept the science must submit to theology. But to do this, he would need to invent a new way of thinking, one that blended observation, mathematics, and skepticism into a systematic process. That process would become the basis of modern science. But before we explore Galileo's methods and discoveries, we must understand one thing clearly. He was not merely a man with a telescope. He was the first to turn the telescope into a scientific instrument. He was not merely a critic of Aristotle, he was the one who put Aristotle's ideas to the test. And he was not merely a thinker, he was an experimenter, a calculator, a physicist in all but name. The world before Galileo was full of certainties inherited from ancient books and unchallenged assumptions. Galileo's world would become one of questions, data, and proof, a world where knowledge could be measured, recorded, and tested by others. And that shift from unquestioned truth to measured reality marks the birth of modern science. Galileo Galilei was born on the 15th of February, 1564, in the city of Pisa, Italy. His birth occurred at a time when the Renaissance was reaching full bloom across Europe, a period defined by rediscovery of classical knowledge, but also by the gradual emergence of something entirely new, a culture of investigation, measurement, and skepticism. Galileo's father, Vincenzo Galilei, was a skilled musician and music theorist. He was also a man with a questioning mind. Vincenzo challenged prevailing musical doctrines of the time, particularly the rigid mathematical ratios inherited from antiquity. He believed that music should be understood, not only through theory, but through direct experience and auditory testing. This subtle rebellion against inherited knowledge and in favor of personal observation left its mark on his son. Galileo was the eldest of 6 children. Though his family belonged to the lower nobility, they were not wealthy. Yet his parents valued education highly, and young Galileo showed early signs of intellectual curiosity. He was initially sent to study at a monastery with the intention of entering the priesthood, but his father had other plans. By the age of 17, Galileo was enrolled at the University of Pisa to study medicine. At the time, medicine was not based on biology or chemistry as we know them today. Instead, it was an extension of ancient texts, chiefly the works of Galen and Hippocrates, interpreted through Aristotelian philosophy. The 4 humours, blood, phlegm, black bile, and yellow bile, were believed to govern health, and treatments like bloodletting were prescribed without empirical validation. Galileo quickly realized he was not interested in this kind of medical theory. What fascinated him instead was mathematics. He was captivated by the logical structure of geometry and the elegance of Euclidean proofs. He began attending lectures on mathematics, against his father's wishes, and soon abandoned medicine altogether. But in Galileo's time, mathematics was not yet considered a foundational science. It was seen as a practical tool useful for astronomy, surveying, architecture, and mechanics, but not as a pathway to understanding nature itself. Natural philosophy, the forerunner of physics, relied on logic and qualitative analysis, not quantitative laws. Galileo began to question this divide. Why should mathematics be excluded from the study of motion and matter? Could geometry and number not describe how the world actually behaves? It was at Pisa where Galileo conducted one of his earliest and most famous demonstrations, though it may never have happened quite the way legend tells it. According to tradition, Galileo climbed the Leaning Tower of Pisa and dropped 2 spheres of different weights to prove that they hit the ground at the same time. This act, whether real or symbolic, was aimed at directly disproving Aristotle's assertion that heavier bodies fall faster than lighter ones. In fact, Aristotle had claimed that the speed of fall is proportional to weight. If one object is twice as heavy as another, it should fall twice as fast. Galileo's counter-argument was not simply verbal. He believed in testing. He rolled balls of different masses down inclined planes, which slowed the motion enough for him to measure time more accurately using water clocks or musical timing. Through repeated trials, he discovered that weight had no effect on the rate of acceleration under gravity. What mattered was time and distance. From these experiments, Galileo derived what we now recognize as the fundamental kinematic equation for constant acceleration. In modern symbols, this is written as c equals 1/2 times g times t squared, where c is distance traveled, g is the acceleration due to gravity, and t is the time elapsed. Galileo discovered this relation not through algebra, which was still developing, but through careful measurement and geometric reasoning. He showed that the distance an object travels while accelerating from rest increases with the square of the time elapsed. This was revolutionary. It replaced vague talk of natural motion with a precise numerical relationship. For the first time, a law of nature had been quantified, not guessed, but measured. But Galileo's thinking extended beyond falling bodies. He began studying pendulums, noticing something curious. If you set a pendulum swinging, it tends to take the same amount of time for each swing, regardless of how far it swings, at least for small angles. This observation is called the isochronism of the pendulum. Galileo realized that the period of a pendulum, the time it takes to complete one full swing, depends only on its length, not on its weight or amplitude of swing, provided the angle remains small. Though he did not have precise formulas, he was on the path to what would later become t equals 2 pi multiplied by the square root of L divided by g, where t is the period, L is the length of the pendulum, and g is the acceleration due to gravity. Galileo's pendulum studies were not just idle curiosity. They laid the foundation for timekeeping devices and demonstrated that motion could be regular and predictable even in a chaotic world. His work began to attract attention, and he was soon offered a position teaching mathematics at the University of Pisa. But Galileo's insistence on challenging orthodoxy made him unpopular. His criticisms of Aristotelian physics and his growing reputation as a disruptive thinker led to tension with his academic peers. Eventually, he left Pisa and moved to the University of Padua, where he would spend nearly 2 decades teaching mathematics, mechanics, and astronomy. It was in Padua that Galileo would refine his experiments, construct better instruments, and begin observing the heavens, turning from the study of motion on Earth to the motion of the cosmos itself. But even in these early years, one thing was becoming clear. Galileo was not content with received wisdom. He demanded evidence. He believed that nature was a book, written in the language of mathematics, and only through observation and deduction could we begin to read it. The young man from Pisa was becoming more than a mathematician. He was becoming a physicist in practice, before the term even existed, a mind that would soon peer through a telescope and forever change what humanity thought it knew about the universe. By the time Galileo Galilei settled into his role at the University of Padua in 1592, his intellectual trajectory had already deviated sharply from the norm. Unlike his contemporaries who echoed Aristotelian explanations, Galileo was beginning to think in terms of cause, effect, and measurement. He was not yet using the term experiment in the modern sense, but the principles were there. He wanted to test assumptions, not by rhetorical argument, but by direct interaction with nature. One of the most powerful ideas Galileo introduced was this: to understand motion, we must observe it under controlled conditions. It sounds simple now, but this was radical in a world where most people still believed that truth was revealed by authority, not discovered by testing. Galileo believed that natural laws could be expressed with mathematical relationships, but to find them he needed a way to slow motion down enough to analyze it precisely. This led him to a series of experiments using inclined planes, smooth, angled wooden ramps that allowed balls to roll slowly under the influence of gravity. By reducing the angle of descent, Galileo could stretch a fall that would normally take 1 second into several seconds, allowing him to observe patterns more clearly. He marked equal distances along the ramp and timed how long it took a ball to roll between each pair of marks. He didn't have a stopwatch. Instead, he used a water clock, a container with a small hole at the bottom. As the ball rolled, an assistant would allow water to flow, then quickly seal the opening when the ball passed a mark. The volume of water collected provided a way to compare time intervals. Through this process, Galileo discovered something that had never been formalized before. The distance traveled by a uniformly accelerating body increases with the square of the time elapsed. In modern terms, this is written as distance equals 1/2 multiplied by acceleration multiplied by time squared. but Galileo expressed it geometrically. Through ratios, he noticed that if 1 second passes, the ball might travel 1 unit of distance. If 2 seconds pass, it travels 4. If 3 seconds pass, it travels 9. 1 squared is 1, 2 squared is 4, 3 squared is 9. This consistent pattern allowed him to define a law of motion, and he didn't stop there. Galileo also began analyzing what we now call uniform acceleration. He realized that for a falling object, its velocity increases constantly over time. This concept defied Aristotle, who had claimed that motion without an applied force was impossible. Galileo showed that objects can continue moving without continuous force, so long as no resistance opposes them. This idea would become the seed for Newton's first law of motion, often paraphrased as, "An object in motion stays in motion unless acted upon by an external force." But Galileo had already laid the groundwork. In one particularly insightful experiment, he imagined a ball rolling down one slope, then up another of equal height. If there were no friction, he reasoned, the ball would roll up to the same height it started from, and if the second slope were stretched out longer and flatter, the ball would still reach the same height, but it would travel farther before stopping. So what if the second slope were infinitely long, completely flat? In that case, the ball would never stop moving at all. Galileo concluded that horizontal motion does not require continuous force to persist, a complete reversal of Aristotelian thinking. He also explored the motion of projectiles, objects thrown or launched through the air. Common wisdom at the time said a projectile moved in a straight line until it ran out of force, then dropped suddenly to the ground. But Galileo, again, working with geometry and observation, found that the path of a projectile is not two straight segments, but a continuous curve. He discovered that a projectile moving under the influence of gravity traces a parabolic path. This is because its motion can be split into two components: a horizontal motion that is uniform, a vertical motion that is uniformly accelerated. Combined, these two motions create a curve, a parabola. This conclusion, drawn without the formal calculus that would later be developed by Newton and Leibniz, showed Galileo's extraordinary intuition and mathematical skill. This was not just theoretical. The study of projectile motion had practical consequences in military ballistics, architecture, and mechanical engineering. By understanding how cannonballs flew or how weights fell, engineers could build better machines, towers, and even timepieces. Galileo's discoveries represented a new kind of thinking. He did not rely on mystical causes or vague categories like heaviness or natural place. He sought to describe how objects move, not why they ought to, and he described that motion with numbers. He was also one of the first to realize the power of systematic experimentation. Instead of testing once and accepting the result, he repeated trials. He changed variables. He looked for patterns that could be replicated. He drew diagrams and recorded his measurements with care. In doing so, he was beginning to outline the scientific method, even before that term existed. Of course, Galileo had his flaws. He sometimes overstated his conclusions. He occasionally dismissed ideas too quickly if they didn't fit his framework. But what distinguished him from his peers was his willingness to question authority, even the authority of tradition, of books, and of ancient minds. And the results were undeniable. He had shown that falling objects accelerate uniformly. He had demonstrated that mass does not affect the speed of fall. He had described projectile motion as a compound of linear and accelerated motion, and he had started to view motion as something that could be measured, modeled, and explained mathematically. He didn't call himself a physicist, but by modern standards, he was one of the first. His early experiments, simple in tools, profound in insight, marked the beginning of the end for Aristotelian physics, and they set the stage for everything that would follow, from Newton to Einstein. Galileo was beginning to build not just a new theory, but a new way of knowing, and as his understanding of earthbound motion deepened, he was about to look upward toward the heavens and apply the same logic, the same instruments, and the same courage to a far greater question: what exactly moves in the sky? Long before the word physics referred to mathematical models and laboratory experiments, people still wondered about the most basic question: why do objects fall? For nearly 2,000 years, the answer was governed by Aristotle's teachings. According to him, objects fall because they are seeking their natural place, a concept tied more to philosophical harmony than physical mechanics. In Aristotle's view, the heavier the object, the faster it should fall. This seemed to align with common sense. A rock falls faster than a leaf. But this comparison ignored an essential factor: air resistance. Galileo Galilei began to question these assumptions not with abstract speculation, but with carefully designed controlled experiments. And in doing so, he founded what we now call kinematics, the branch of mechanics that describes motion without considering its causes. To study falling motion in a controlled way, Galileo returned to his inclined planes. By adjusting the angle of the ramp, he could vary the component of gravitational acceleration, making motion slower and easier to measure. The more shallow the slope, the less acceleration occurred. This allowed him to study gravity in slow motion. Galileo marked equal distances along the ramp and measured the time it took a rolling ball to pass each segment. Through multiple trials, he discovered a consistent pattern. The distance covered was not linear with time. It was quadratic. That is, distance is proportional to time squared. In words, this means that if you double the time an object is allowed to fall, it will fall 4 times as far. Triple the time, and it will fall 9 times as far. Expressed in modern terms, Galileo was approaching the equation distance equals 1/2 multiplied by gravitational acceleration multiplied by time squared. He didn't write it that way, because algebraic notation was still primitive, but his geometric diagrams and ratios expressed exactly this relationship. This single insight, acceleration being uniform and distance increasing with the square of time, marked a fundamental break from ancient physics. Aristotle had said that an object reaches a fixed speed, determined by its weight. Galileo showed that falling objects do not reach speed, they gain speed as they fall. That gain in speed, what we now call acceleration, is constant for all objects in a vacuum, and most importantly, it is independent of mass. This was an astonishing idea. A cannonball and a musket ball dropped from the same height fall at the same rate, not because of their shape, but because gravity acts equally on all masses, provided no air resistance interferes. To test this, Galileo conducted rolling ball experiments in which he changed the mass of the ball while keeping its size constant. He found that heavier and lighter balls took the same amount of time to descend the ramp. This directly contradicted Aristotle's claim that heavier objects fall faster. Though he could not yet eliminate air resistance in real life, Galileo understood the principle of idealization. He reasoned that in the absence of air, or any resisting force, all objects would fall at the same rate under gravity. This led to a deeper concept. Free fall is universal, whether it's a feather, a hammer, or a mountain dropped from orbit. The acceleration is the same. On Earth, this value is approximately 9.8 meters per second squared. Galileo didn't know the exact number, but he understood the concept of uniform gravitational acceleration. That was more important. He also noted that speed increases linearly with time during a fall. That is, final velocity equals gravitational acceleration multiplied by time, or in modern notation, v equals g times t. But again, Galileo preferred ratios and geometry over equations. He saw that as time doubled, velocity doubled. As time tripled, velocity tripled. This relationship was linear, even though distance grew with the square of time. That distinction between velocity and displacement was something new to science. Galileo also investigated the instantaneous speed at each point along a ramp. He did this by attaching bells along the track, spaced such that they would ring in equal time intervals as the ball rolled. The sound pattern helped him verify the acceleration rate. Closer bell tones meant increasing speed. This experiment was ingenious. It turned time into and it helped Galileo visualize acceleration before there were high-speed cameras or digital timers. All of this experimentation contributed to a new concept of motion, that motion could be defined, measured, and predicted by laws of mathematics. Kinematics had begun. Galileo wasn't describing why gravity existed. That would come later, with Newton, but he was describing what gravity does to moving bodies, and he was doing it with consistency, repetition, and quantification. This was something Aristotle had never done. For Aristotle, nature was full of purpose. Objects moved because they had an internal tendency. Rocks fell because they wanted to be on the ground. Fire rose because it sought the heavens. But Galileo replaced this language of intent with the language of mechanics. He didn't ask what an object wanted to do. He asked how fast it moved, how far it traveled, and how time and motion could be related. This shift in language, this rejection of teleology, was one of Galileo's most profound contributions. He also noticed something surprising about symmetry in motion. When a ball rolls down a ramp and then up a second ramp of equal height and angle, it returns almost to its original height unless friction intervenes. This implied that the ball conserved its energy of motion. Although Galileo didn't formulate energy conservation explicitly, he intuited the idea of reversibility and kinematic symmetry, ideas that would eventually evolve into the principle of conservation of mechanical energy. It was clear, Galileo was not just disproving Aristotle, he was building an entirely new science. A science in which falling wasn't about nature or weight, but about time, distance, acceleration, velocity, and crucially, where the mathematical structure of motion could be determined without knowing what caused it. This is what defines kinematics, the study of how things move, without asking why. Galileo was now able to predict how far an object would fall in a given time, how fast it would be moving at any moment, how long it would take to reach the ground from a given height, all through experimentation, repeated measurement, and geometric modeling. Even though calculus was still a century away, Galileo was laying the groundwork for it. His understanding of motion anticipated the concepts of limits, rates of change, and differential relationships. He saw motion not as a single event, but as a continuous process, governed by rules that could be discovered. By the end of this phase of his work, Galileo had transformed the question, "Why do objects fall?" into a much more precise inquiry. How does the distance fallen relate to time, and how can we predict it? He had shown that falling is not a mystery, it is a measurable, consistent, and mathematical phenomenon. And that, in many ways, was the beginning of physics. In the late 16th century, timekeeping was still an art, not a science. Clocks were built with gears and springs, but their accuracy was limited. Some used water flow, others relied on escapements driven by weights, but none of them offered the regular, predictable rhythm that modern science demands. Galileo Galilei changed that, not by inventing a new mechanism, but by noticing a pattern in something ancient and simple, a swinging lamp. According to his own notes, Galileo first observed the regularity of pendulum motion while watching a chandelier swaying in the Cathedral of Pisa. He noticed that no matter how wide or narrow the swing, the time it took to complete one oscillation remained nearly constant, at least for small angles. This property would later be called isochronism, from the Greek word isos meaning equal and chronos meaning time. To test his observation, Galileo began building pendulums using cords and metal weights. He counted the swings by synchronizing them with his pulse. A crude but effective method. He found that for small displacements, the pendulum's swing period did not change significantly, even if the arc varied. This was significant. It suggested that the pendulum could be used as a natural timekeeper, a mechanism defined not by human engineering, but by the physics of motion itself. Let us consider the physics involved. When a pendulum swings, it converts potential energy into kinetic energy and back again. At the highest point in its swing, the bob has maximum potential energy and zero velocity. As it falls, that potential energy is converted into motion. At the lowest point, the energy is entirely kinetic. Then the process reverses. The time it takes to complete one full swing, called the period, depends primarily on the length of the pendulum and the gravitational acceleration acting on it. In modern terms, we describe the period with this equation. Period equals 2 pi multiplied by the square root of the length divided by gravitational acceleration, or in text-to-speech format, the time for one swing equals 2 times pi times the square root of the pendulum's length divided by gravity. This relationship is elegant, and it shows that mass does not affect the period. A heavy pendulum and a light one of equal length will swing at the same rate, assuming air resistance is negligible and the angle is small. Galileo didn't have this exact equation, but he recognized the dependency between length and time. He also understood that a pendulum's swing could serve as a unit of time, a repeatable, observable cycle in nature. This observation was revolutionary. It meant that time could be measured not by the decay of water, not by the spinning of gears, but by the laws of motion. Galileo had identified something universal and mechanical in a world that still treated time as fluid and imprecise. He envisioned a future where pendulums regulated clocks, making them accurate enough for science, navigation, and astronomy. He even designed a prototype of a pendulum-driven timepiece, though it wasn't constructed in his lifetime. That would wait until the Dutch scientist Christian Huygens, who built the first successful pendulum clock in 1656, decades after Galileo's death. Still, the conceptual leap was Galileo's. He had transformed the swinging weight, an object of casual observation, into a tool for measuring reality. He connected motion and time in a consistent mathematical way. But Galileo's study of pendulums was not limited to clock. It also deepened his understanding of harmonic motion, a type of oscillation that appears in springs, sound waves, and even planetary orbits. He recognized that pendulum motion is periodic. It repeats at fixed intervals, and he understood that such systems could be modeled mathematically, long before the development of trigonometry-based solutions or differential equations. In modern physics, we described simple harmonic motion with the equation acceleration equals negative omega squared multiplied by displacement, where omega is the angular frequency of oscillation. In voiceover terms, acceleration is proportional to the negative of position, meaning the restoring force always points toward the center. This is the mathematical signature of a harmonic oscillator, and the pendulum is the simplest mechanical example. Galileo didn't express this in formulas, but his intuition was correct. He saw that the pendulum was governed by laws, not chance, and he used it to develop more than timekeeping. He used it to validate his entire approach to physics. In later work, Galileo used pendulums to study reaction time, distance estimation, and even musical rhythm. He tied together the physics of motion, the structure of time, and the perception of order, and the broader implication was profound. If motion could be measured, and time could be regular, then the universe itself might be governed by patterns we could uncover, not just describe, but predict. The pendulum was not just a swinging mass, it was a symbol of Galileo's worldview, that the natural world was intelligible, quantifiable, and rule-bound, that it could be known through observation, reason, and mathematics. Even today, the pendulum remains a classroom staple, not just because it's easy to build, but because it reveals something fundamental, something that Galileo was the first to truly see. That motion has memory, that time has structure, that nature repeats itself not by chance but by law. And so from the quiet swing of a chandelier, Galileo extracted a pattern that would influence generations of scientists, engineers, and clockmakers. By the early 1600s, Galileo Galilei had already overturned several core assumptions of Aristotelian physics. He had shown that objects fall at the same rate regardless of mass, that falling bodies accelerate uniformly, and that pendulums swing with predictable regularity. But there was one form of motion that remained misunderstood, one that combined horizontal movement with vertical fall. It was the motion of a projectile. In the Aristotelian model, projectile motion was divided into two phases. First, there was an impressed force, a push, that moved the object in a straight line. Once that force ran out, the object would fall straight down in a natural vertical motion. To Aristotle, the transition was abrupt and undefined. A cannonball flew forward, then suddenly dropped. No curve, no unity between the phases. Galileo rejected this division. He proposed a new framework, that projectile motion is a single continuous process, governed by two independent components: a horizontal component, which moves at constant velocity, a vertical component, which accelerates under gravity. Together, these two motions combine to form a curve, and not just any curve, but a parabola. Let's break this down using Galileo's logic. Imagine a ball rolling across a flat surface. If there's no friction, it continues at a steady pace. This is uniform horizontal motion. Now imagine the same ball is dropped from a height. It begins to fall, picking up speed at a constant rate. This is vertical acceleration. Now combine the two. Roll the ball off the edge of a table. It continues moving forward at the same rate it had on the table, but now it also begins to fall. The result is a path that curves downward, and that path can be described mathematically. In modern terms, we define the horizontal distance traveled as horizontal distance equals horizontal velocity multiplied by time, and we define the vertical displacement as vertical distance equals 1/2 multiplied by gravity multiplied by time squared. When plotted together, these equations produce a parabolic trajectory, a curve where the vertical drop increases with the square of the time, while horizontal distance increases linearly. Galileo didn't write these equations using symbols, but he expressed the relationship clearly in geometric terms, using diagrams and ratios. He showed that if you trace the position of a projectile at equal time intervals, the points form a parabola. This was one of the first times anyone had analyzed motion in two dimensions. Previously, vertical and horizontal movements were treated as separate phenomena. Galileo united them through superposition, a key concept in modern physics, which says that independent motions can be added together to describe the total motion. Galileo's insight laid the foundation for understanding ballistics, the science of projectile motion. Whether firing a cannon or throwing a stone, the same principles apply, and they are predictable. He even calculated the optimal angle for launching a projectile to achieve maximum range. That angle is 45 degrees, assuming no air resistance and a flat surface. This had clear military applications. Artillery officers who understood parabolic motion could aim more accurately, hit more distant targets, and optimize the angle of fire. But more importantly, this analysis turned the behavior of a cannonball into a mathematical system. A real-world physical process, violent and fast, could be described precisely, using equations and logic. In this way, Galileo moved the study of motion from the realm of philosophy into the realm of mathematics. He no longer asked what motion meant, he asked how it behaved, and how it could be described with numerical consistency. This shift was more than technical, it represented a change in worldview. If the flight of a cannonball could be predicted, so could the fall of a planet. If physical forces obeyed laws, then nature itself might be lawful. Galileo began to suspect that all of physics, earthly and celestial, could be described mathematically. But there was a problem. Galileo had no formal tools to handle variables that changed with time. Calculus had not yet been invented. Still, he worked around this limitation by using limiting arguments, reasoning about how quantities behave as time becomes very small. He considered very short intervals of time, and looked at how displacement, velocity, and acceleration behaved across those intervals. In doing so, he laid the conceptual groundwork for calculus, even if the symbols would come later. The modern calculus-based equation for the range of a projectile is range equals initial velocity squared, multiplied by the sine of 2 times the angle, divided by gravity, spoken in TTS-friendly format. The total distance a projectile travels is equal to the square of its launch speed, multiplied by the sine of 2 times the launch angle, and then divided by gravitational acceleration. Galileo didn't know this formula, but he knew the relationship it described. He used geometry, triangles, and symmetry to explain why projectiles launched at complementary angles, like 30 degrees and 60 degrees, landed at the same point. In doing so, Galileo demonstrated that natural motion was neither chaotic nor mystical. It followed principles, those principles could be tested, and they produced results that matched observation. This approach, build a model, measure the outcome, refine the theory, is the core of modern physics. Galileo's analysis of projectile motion also helped dismantle the old idea that terrestrial and celestial physics were separate. If a cannonball followed a curve, and a moon circled a planet, perhaps both were expressions of the same principle, one that would later be called universal gravitation. Galileo didn't formulate that law, but by showing that even a simple object in flight obeyed a curve, he provided the bridge between earthbound motion and celestial dynamics. And by doing it without invoking divine purpose or final causes, he made physics a matter of experiment and explanation, not belief. To summarize, Galileo's work on projectile motion introduced several critical ideas. Motion in 2 directions can be analyzed independently. Horizontal motion is uniform, vertical motion is accelerated. The combination of these produces a parabolic trajectory. The shape and range of that trajectory can be predicted mathematically, and most importantly, nature behaves consistently, even in dynamic, violent events. From cannonballs to comets, motion follows rules. Galileo showed us how to find them. In the ancient view, motion was something that needed to be explained, not in terms of how it happened, but why. And according to Aristotle, every motion had a purpose, a direction, and most of all, a cause. If a cart was moving, something must be pushing it. If an arrow flew through the air, some force must still be acting on it. And if that force stopped, the object should stop immediately. Motion without a cause, to Aristotle, was impossible. This idea dominated science for over 1,000 years, but Galileo Galilei saw a flaw, not through pure speculation, but through observation and logical reasoning. He began by asking a deceptively simple question. If you slide a ball across a smooth surface, what happens? On rough ground, it slows down quickly. On polished marble, it travels farther. If you reduce the resistance further, if you imagine a perfectly smooth surface with no friction at all, the ball would keep rolling forever. This insight was revolutionary. Galileo realized that it wasn't force that maintained motion, it was friction that interrupted it. The natural state of an object once set in motion is to remain in motion unless something interferes. This was a complete reversal of Aristotelian logic. Aristotle claimed rest was the natural state. Galileo proposed that uniform motion is just as natural as rest. He had discovered the first glimpse of what we now call inertia. Let's define this more precisely. Inertia is the tendency of an object to resist changes in its state of motion. If something is still, it wants to stay still. If it's moving, it wants to keep moving in the same direction and at the same speed. Galileo didn't yet use the word inertia, but his work set the foundation for it. He observed that when objects slow down, it's not because motion decays, it's because external forces like friction, air resistance, or impact oppose that motion, remove those forces, and the motion continues. One of Galileo's most famous thought experiments involved two inclined planes. Imagine a ball rolling down one ramp, then up another of equal slope and height. It rolls up to nearly the same height it started from, losing only a bit of energy due to friction. Now make the second ramp shallower. The ball still reaches the same height, but travels a longer distance. Now imagine that second ramp becomes completely flat, no slope at all. What happens? The ball no longer climbs, but it also doesn't stop. It continues moving indefinitely, maintaining its velocity. This thought experiment was more than clever. It was conceptually profound. Galileo was showing that no ongoing force is required to sustain horizontal motion. The only reason we see things slow down is because real-world surfaces aren't frictionless. Galileo's reasoning anticipated Newton's first law of motion, which would later be written as, "An object in a state of rest or uniform motion will remain in that state unless acted upon by an external force." In text-to-speech format, an object at rest stays at rest, and an object in motion stays in motion unless a force changes that state. Galileo never formalized this law as Newton would, but the core idea was his. He was transitioning physics away from the idea of objects needing force to stay in motion, and toward the idea of motion as a default condition, only altered by external factors. This required a new understanding of force. Force was no longer what sustained motion. Force became what changed motion, what caused acceleration, not velocity. And that redefinition reshaped all of mechanics. Galileo's insight told scientists that the absence of change, constant speed in a straight line, meant no net force. It helped separate the concept of motion from the concept of cause. This separation is what made predictive physics possible. It allowed thinkers like Newton to develop a complete system of dynamics, where force and acceleration are mathematically related. But again, the spark was Galileo's, planted in a time when even imagining endless motion was controversial. This concept of inertia would also become central in astronomy. It helped explain planetary motion. If a planet moves through space, what keeps it going? The answer, Galileo suggested, was nothing. Once set at motion, an object in the vacuum of space would continue in motion, unless acted on by gravity or some other force. This challenged the old idea that heavenly bodies were pushed by invisible spheres or guided by divine forces. It suggested that planets moved by inertia, governed by the same physical laws as objects on Earth. This unification of celestial and terrestrial physics was a profound philosophical shift. Galileo was inching toward the idea that all of nature obeys the same rules, that the laws of motion are not different for stars and stones but universal. In everyday life, inertia explains countless observations. A book sliding across a desk comes to rest, not because motion dies, but because friction removes energy. A passenger in a car lurches forward when it stops, not because of some mystery, but because their body continues in motion while the vehicle decelerates. A satellite in space orbits the Earth, not because it's being pushed forward, but because it's falling continuously while moving sideways, with no air resistance to slow it down. These insights are now part of every physics textbook, but they began with Galileo rolling balls down ramps, watching how they moved and asking what happens when nothing interferes. Galileo didn't invent inertia, but he discovered it, in the most important way, by thinking beyond what his senses showed him, and imagining ideal conditions that could reveal the laws beneath. This required both observation and abstraction, a combination that defines the best of science. With inertia as a foundation, Galileo was now ready to apply his physics to more complex systems, first with inclined planes and parabolas, and soon with telescopes aimed at the night sky, because the next step in his journey was not about rolling objects, it was about celestial bodies. In the early 17th century, Europe was just beginning to experiment with a novel invention, the telescope. Originally developed in the Netherlands, it was a crude device used by merchants and sailors to see distant objects. But when Galileo Galilei first heard of this device in the year 1609, he immediately saw something others did not. He didn't just see a spyglass, he saw a scientific instrument, a tool to uncover truths about the universe. Galileo did not invent the telescope. That credit goes to Dutch opticians like Hans Lippershey. However, Galileo rapidly improved its design. Using his deep understanding of geometry and optics, he began grinding lenses himself, experimenting with focal lengths, curvature, and alignment. His goal was simple: to build a telescope that could magnify more than any commercial version and make it clear enough to observe the heavens. Within months, Galileo had built a telescope that could magnify objects 8 times, and soon after, he refined the design to reach 20 times magnification. At the time, this was extraordinary. Let us consider what made this possible. A basic telescope of Galileo's time used 2 lenses: a convex objective lens, which gathered and bent incoming light, a concave eyepiece lens, which magnified the image for the observer. This design is now called the Galilean telescope. The magnifying power of a telescope depends on the ratio of the focal length of the objective lens to the focal length of the eyepiece. In text-to-speech terms, magnification equals the focal length of the objective lens divided by the focal length of the eyepiece lens. By crafting lenses with carefully chosen curvature and spacing, Galileo optimized this ratio, achieving a level of clarity never seen before. But building the telescope was only part of the story. The real revolution came when Galileo turned it upward toward the sky. Prior to this, few had thought to use optical instruments to study celestial bodies. The heavens, according to religious and Aristotelian belief, were already known. They were perfect, unchanging, and composed of a special, incorruptible substance called ether. Galileo's telescope shattered that illusion. In 1610, he aimed his lens at the moon, an object long believed to be a flawless, smooth sphere. What he saw stunned him. The moon was not smooth. It was irregular, scarred, and mountainous. Galileo observed light and shadow playing across its surface. The patterns were not random. They revealed ridges, craters, and elevations. By studying how shadows moved across the lunar surface, Galileo even estimated the height of the mountains, concluding that some peaks were several kilometers tall. This was a direct contradiction of the ancient belief that celestial bodies were perfect and unchanging. If the moon had mountains like Earth, then it wasn't made of divine material, it was geologically real. Galileo sketched what he saw, producing detailed lunar drawings that were unlike anything the public had seen. For the first time, people could see the moon as it truly was, not a mystical light in the sky, but a physical object. But Galileo did not stop at the moon. In January of 1610, he turned his telescope toward Jupiter. What he saw next would become one of the most important discoveries in the history of astronomy. He observed 4 tiny points of light near the planet, points that changed position night after night. At first he thought they were fixed stars, but soon it became clear these points were moons, orbiting around Jupiter. Galileo had discovered that not everything revolved around the Earth. These 4 bodies, now known as the Galilean moons, Io, Europa, Ganymede, and Callisto, demonstrated that a planet other than Earth could have its own satellite system. This dealt a serious blow to the geocentric model, which held that Earth was the fixed center of all celestial motion. In a heliocentric system, where planets orbit the Sun, Jupiter having moons made perfect sense. But in the Ptolemaic model, it was a complication that could not be ignored. Galileo had gathered empirical evidence that the Earth was not unique in having orbiting bodies, and therefore the Earth was not necessarily the center of all motion. Galileo continued observing other phenomena as well. He noted the phases of Venus, which, like the moon, waxed and waned. This was especially significant. In the Ptolemaic system, Venus always remained between Earth and the Sun, and could never show a full phase. But Galileo observed Venus as a crescent, a half phase, and eventually nearly full. This observation could only be explained if Venus orbited the Sun, not Earth. It was geometric proof in favor of heliocentrism. These discoveries were not theoretical arguments. They were visual data gathered through observation, using a device that Galileo had turned into a tool of science. With every new observation, sunspots, star clusters, planetary disks, Galileo reinforced a new idea that the universe was not centered on Earth, that the heavens were not perfect, and that empirical tools could lead to truth far beyond what ancient texts had imagined. In 1610, Galileo published his findings in a short but powerful book titled Sidereus Nuncius, or the Starry Messenger. It contained descriptions of the moon's surface, the moons of Jupiter, and the density of stars in the Milky Way. Galileo also revealed that the Milky Way, previously seen as a cloudy band, was in fact composed of countless individual stars too faint to see with the naked eye. The book was a sensation. It was clear, illustrated, and scientifically grounded. It marked a new kind of astronomy, one based not on celestial harmony or religious doctrine, but on observation, measurement, and evidence. but it also caused controversy. Many scholars refused to look through Galileo's telescope. Some claimed the instrument caused illusion, others denied the evidence entirely, arguing that the perfection of the heavens was a theological truth, not a matter of optics. Still, the damage to old ideas had been done. Galileo had proved that the telescope could do more than magnify. It could reveal. It could challenge belief. It could expose the structure of reality to careful, rational eyes. But for Galileo, the telescope was not a toy or a weapon. It was a philosophical instrument, a way to test hypotheses, to gather data, and to replace speculation with knowledge. He had built a better telescope, and in doing so he had built a better method for understanding the cosmos. The age of naked-eye astronomy was ending. The age of instrumentation, measurement, and experimental verification had begun. For much of human history, the moon was considered a symbol of purity, a flawless celestial sphere that reflected divine perfection. In Aristotelian cosmology, all heavenly bodies were believed to be smooth, unchanging, and composed of a perfect element called aether. Imperfection, irregularity, and ands were qualities reserved for the earth, not the skies. But in the year 1610, when Galileo Galilei turned his newly refined telescope toward the moon, he saw something that directly contradicted this belief. What he observed was not a perfect orb. He saw shadows. He saw ridges. He saw structure. What Galileo witnessed were mountains, valleys, and craters. Topographical features that suggested the moon was not made of divine substance but rather shared physical properties with Earth. This was one of the first times a human being looked into the night sky and saw not myth but geology. Let us understand the observational method Galileo used. Using a telescope with a magnification of about 20 times, he focused on the terminator, the line that separates the illuminated portion of the moon from the shadowed portion. Along this boundary, Galileo noticed irregular shapes, jagged edges where the light faded unevenly. These patterns indicated elevations, regions where sunlight hit peaks, while surrounding areas remained in darkness. From this, Galileo deduced that the moon's surface was uneven. He began sketching what he saw. His drawings, now preserved in Sideris Nuncius, show crescent moons textured with light and dark regions, resembling mountain ranges at sunrise. But Galileo went further than sketching. He attempted to measure the height of the lunar mountains. How? He used the length of the shadows they cast. Just as a mountain on Earth casts a shadow during sunrise or sunset, so do lunar mountains when sunlight strikes at an angle. Galileo reasoned that the length of the shadow, combined with the angle of the sun, could be used to estimate the elevation of these features using basic trigonometry. He concluded that some lunar peaks rose over 4 miles high, comparable to the tallest mountains on Earth. This measurement, performed from Earth through a lens in the early 17th century, was an extraordinary example of applied geometry in astronomy. These observations were not only accurate, they were subversive. They directly challenged the idea that the heavens were fundamentally different from Earth. If the moon had mountains and craters, then perhaps it was made of similar material. Perhaps it had formed through natural processes. Perhaps it was not a perfect sphere, but a world like ours. This was a cosmological revolution in miniature. The Earth was no longer unique in its imperfection, and the moon was no longer a spotless silver disk. It was a complex object, governed by the same physical laws that applied here. Galileo also observed the moon's albedo features, the bright and dark areas across its surface. He noted that the lighter regions, now called the lunar highlands, appeared rough and mountainous, while the darker areas, known today as the lunar maria, were flatter and less reflective. He didn't know the exact nature of these regions, but he documented them carefully, suggesting they might be seas or plains. These weren't vague impressions, they were systematic observations, recorded over many nights, across various lunar phases, using a telescope he had built himself. And these observations raised more questions. If the moon was not perfect, what about the other planets? What about the sun? Galileo began to suspect that imperfection, not perfection, might be the natural state of celestial objects. And if that were true, then the line between the heavens and the earth, long held to be sacred and absolute, was beginning to blur. This idea was not new in science, but Galileo made it visible. He didn't just argue against the old models, he provided direct evidence, and that evidence could now be shared. Anyone with a telescope could repeat his observations. Anyone could see the shadows on the moon and witness the truth for themselves. This was one of Galileo's most important legacies. the idea that nature could be verified through instrumentation and replication. It was no longer enough to reference Aristotle. One had to look, measure, and compare. And this shift from inherited wisdom to empirical data is what separates modern science from ancient philosophy. Galileo's moon was more than a scientific object. It was a symbol, a gateway into a universe governed by the same principles everywhere. It told us that the moon had elevation and depth, and that even the most revered beliefs could be overturned by evidence. Today, when we look at the moon through binoculars or photographs taken from orbit, we take for granted that it is a rocky world. But in Galileo's time, even the suggestion that it was imperfect bordered on heresy. Yet with a telescope of wood and glass and the courage to publish what he saw, Galileo revealed the first non-Earth terrain ever mapped by a human being. Not with satellites, not with rockets, but with reason, optics, and the refusal to accept tradition without question. In the early 17th century, the sun was regarded not just as a source of light, but as a symbol of divine perfection. It was believed to be immaculate, unchanging, and made of an ethereal substance untouched by decay or imperfection. In the Aristotelian model, the sun was not just physically perfect, but theologically necessary to remain so. Then Galileo Galilei pointed a telescope at it. What he saw would once again challenge centuries of belief. The sun, like the moon, was not flawless. It was dynamic. It was alive with activity. In 1611, Galileo began observing the sun through a technique known as projection. Rather than looking directly at the sun, which would be dangerous, he directed sunlight through the telescope onto a flat white surface, projecting an enlarged image. This allowed him to safely record details about the sun's surface. What he found were sunspots, dark patches that appeared, moved, and sometimes vanished over time. To some, these spots were defects in the telescope lens. To others, they were planetary bodies transiting the solar disk. But Galileo ruled out these possibilities through repeated, systematic observation. He tracked the motion of sunspots from day to day, noting that they moved across the surface of the sun in a consistent pattern. After about 2 weeks, the spots disappeared, only to return on the opposite side, moving again in the same direction. This strongly suggested one thing: the sun was rotating. Let's clarify what Galileo discovered. Sunspots appeared dark because they are cooler than the surrounding solar surface. Though Galileo didn't know the physical reason, he could still observe their movement. By tracking their position over several days, he estimated that the sun completes one full rotation, approximately every 25 to 30 days, depending on latitude. This was direct evidence that a celestial body, not just Earth, undergoes physical motion, and that its surface is not perfect, but marked and variable. In modern astronomy, we now understand that sunspots are caused by intense magnetic activity on the sun's surface. These regions temporarily inhibit convection, reducing surface temperature and appearing darker against the surrounding brightness. But Galileo didn't need to understand the mechanism. His achievement was in the method. Observe, record, analyze over time, infer physical behavior. He published his findings in a series of letters compiled under the title Letters on Sunspots, or Storia e dimostrazioni intorno alle macchie solari. These letters, addressed to another scientist, Christoph China, laid out Galileo's arguments that sunspots were on or near the solar surface, and not planets or shadows from Earth. This was a dangerous position to hold, because if the sun, a symbol of divine perfection, was proven to be imperfect, then the heavens were no longer sacred in the Aristotelian sense. If change occurred in the sun, it could occur anywhere, and if celestial objects could change, decay, or move like earthly bodies, then the separation between heaven and earth was gone. Galileo's observations also added to his growing conflict with religious authorities. To many church figures, the sun had theological meaning. It was God's eye, God's creation, God's eternal flame. Galileo was not only redefining its structure, he was secularizing it. Yet he persisted, because the evidence was clear. He observed that sunspots were not fixed. They changed in shape. They grew and shrank. Some broke into fragments. Some coalesced. All of them moved in sync with the sun's rotation. This wasn't symbolic interpretation. It was data. By carefully sketching sunspots day after day, Galileo created time-lapse sequences that showed the dynamic behavior of the sun's surface. He proved that even the brightest object in the sky was subject to physical law, variation, and observation. In modern terms, the sun's rotation is differential, meaning it rotates faster at the equator than at the poles. Galileo couldn't detect this differential rotation, but he did recognize that the sun was not static. His observations showed that it completed a full rotation in roughly 27 days, as seen from Earth. This measurement was remarkably accurate, considering the tools of the time. Galileo's ability to extract quantitative knowledge from qualitative observations is a testament to his scientific intuition. Sunspots also had broader implications. They revealed that light itself was not evidence of perfection. That brightness did not mean purity. That the most important body in the sky, central to life, time, and theology, was a physical object, subject to the same rules as falling bodies, swinging pendulums, and rolling balls. In Galileo's worldview, the sun was no longer a symbol. It was a rotating sphere of matter, a dynamic system that could be studied, measured, and explained. This conclusion fit perfectly with his broader scientific philosophy, that truth is not revealed through tradition, but through instruments, measurement, and logical inference. And the more Galileo looked, the more he saw a universe not of divine perfection, but of patterned imperfection, a cosmos bound by laws, not insulated by mysticism. From Earth's falling apples to the sun's rotating face, nature was governed by motion, structure, and regularity, and the telescope had become the eye, through which science could begin to see the universe as it really was. Galileo had now made direct observations of the moon's mountains, the phases of Venus, the moons of Jupiter, and the sunspots that danced across the solar surface. Each of these findings built a cumulative case. The cosmos was not fixed. It was not perfect. It was active, complex, and comprehensible. And for the first time in history, a scientist was building that understanding not from philosophy, but from systematic observation with diagrams, time series, and repeatable results. This was not just astronomy, it was the birth of astrophysics. In the spring of 1610, Galileo Galilei did something that would change the course of scientific communication forever. He published a small book, only around 30 pages long, written in Latin and printed in Venice. Its title was Sidereus Nuncius, which translates to the Starry Messenger. This was not a philosophical treatise. It was not a summary of ancient wisdom. It was something new. A first-hand report of telescopic observations, grounded in empirical evidence, explained clearly, and accompanied by diagrams and illustrations. It was a scientific document, and it would shock Europe. To understand the impact of the Starry Messenger, we must understand what made it different. Before Galileo, most astronomical writing was based on mathematical astronomy or philosophical speculation. Ptolemy's epicycles were used to calculate planetary positions, but they were not based on direct observation through instrumentation. With this book, Galileo was claiming that he had seen things no one else had ever seen before. He was not asking readers to believe him based on argument. He was asking them to look through a telescope and verify the facts for themselves. This was science as testable reality, not as authority. The Starry Messenger begins with a brief explanation of the telescope itself. Galileo describes how he constructed his own instruments, improving upon the basic Dutch design. He explains the principles of magnification and lens curvature, and how his telescope could enlarge objects up to 20 times their original size. Then he begins to describe what he has observed through that instrument. First, the moon. Galileo explains in detail that the moon is not a smooth sphere as previously thought, but a rugged, mountainous world. He describes the terminator line, the boundary between light and shadow on the moon's surface, and how the irregularity of this line reveals elevations and depressions. He even estimates the heights of lunar mountains by analyzing the length of shadows cast by peaks at sunrise and sunset. This was stunning to Galileo's readers. The moon was no longer a perfect heavenly body. It was a physical object, like Earth, subject to the same geometry of light and shape. Next, Galileo turns to his most groundbreaking discovery, the moons of Jupiter. He recounts how, while observing Jupiter night after night, he noticed to see small stars close to the planet. The next night, they were in different positions. A few nights later, he saw a fourth. Over time, he realized these were not fixed stars. They were orbiting Jupiter. This was astonishing. In the geocentric model of the universe, all motion was supposed to center around the Earth. The idea that another planet could have its own satellites was unthinkable. Galileo described their movement with precision. He recorded their relative positions each night. noting when they passed behind or in front of Jupiter. He correctly deduced that they were in circular orbits held by Jupiter's gravitational influence. He called them the Medicean stars in honor of Cosimo de' Medici, the Grand Duke of Tuscany, an astute political move to gain patronage. Today, we know these four objects as the Galilean moons, Io, Europa, Ganymede, and Callisto. Galileo's observations of these moons had massive implications. They proved that not everything revolved around the Earth. They supported heliocentric theory by showing that orbital motion was not Earth-exclusive, and they presented the first example of a subsystem, a set of celestial objects orbiting a body other than Earth. Galileo's next observation in the book involved the Milky Way. To the naked eye, it appears as a faint glowing band stretching across the night sky. For centuries, it had been interpreted as a kind of cosmic mist or celestial vapor, but through the telescope, Galileo saw that the Milky Way was composed of countless individual stars. He wrote that the Milky Way was a congeries of innumerable stars grouped together in clusters too small and dense to be seen separately by the naked eye. In other words, what seemed like a blur was actually a vast star field, extending far into the depths of space. This implied that the universe was far more populated and far larger than previously imagined. And finally, Galileo commented on the surface of stars and planets. He noted that stars, when magnified, appeared as points of light, with no discernible shape, while planets appeared as small disks, solid and tangible. This helped distinguish the fixed stars of deep space from the wandering planets within our solar system. All of this, moon craters, Jupiter's moons, star clusters, was presented not as speculation but as observation, and that was the key difference. Galileo had seen these things, he had drawn them, and he invited others to verify them. This approach was unheard of. Instead of deferring to ancient texts, Galileo encouraged others to use instruments to observe, to test, and to repeat. This was the empirical method, the seed of modern science. The starry messenger spread rapidly. Copies circulated throughout Italy, France, Germany, and England. Some scholars were skeptical, others were captivated. Many astronomers began building their own telescopes to test Galileo's claims. Those who did often confirmed what he had seen, but not everyone was pleased. The Church had tolerated Copernican theory as a mere mathematical convenience, not a physical reality. Now, Galileo's findings made that theory observable. The phases of Venus and the moons of Jupiter challenged geocentrism. The imperfect moon and spotted sun challenged theology. Some opponents claimed that the telescope was unreliable, that it introduced optical illusions, that it was distorting God's perfect creation. But Galileo anticipated this criticism. In The Starry Messenger, he offered detailed descriptions, step-by-step observations, and invited replication. He suggested that doubters could borrow his telescope or build their own. This was the scientific spirit, not to declare dogma, but to propose tests. Galileo's writing style in The Starry Messenger was also revolutionary. It was clear, concise, and vivid. Instead of burying his claims in abstract language or academic formalism, he wrote with clarity and urgency. He wanted people to understand what he had seen, and to see it for themselves. His drawings of the moon were detailed and realistic. His tables of Jupiter's moons were systematic and data-driven. His descriptions of the Milky Way were poetic but precise. The Starry Messenger was not just a scientific work, it was an invitation to a new worldview. It marked a shift in how knowledge was created and shared. Before Galileo, knowledge flowed downward from authority to reader. With Galileo, knowledge became collaborative, shared, tested, and open to revision. The Starry Messenger taught Europe how to look through a lens and see truth, not in doctrine, but in data. It also marked the beginning of Galileo's public identity as both a scientist and a challenger of orthodoxy. He was now a celebrity in the world of letters and learning. He gained patrons, critics, and followers, but he also gained the attention of the Church. His telescope had shown people the moon's craters. Soon, it would bring him to the edge of heresy. But before that confrontation, Galileo would go further. He would observe the phases of Venus, the rotation of the Sun, and the motion of Saturn. He would publish more arguments, and eventually, he would write his most dangerous book. But it all began here with a 30-page pamphlet, a short book that told readers, "This is what I saw. You can see it too, and it changes everything." Sidereus Nuncius was more than a report. It was a manifesto, a declaration that the universe was knowable, testable, and far more vast than imagined. And it marked the moment when modern science began to speak in its own voice. By the year 1611, Galileo Galilei had already disrupted centuries of belief. He had revealed that the moon was not a perfect sphere, that the sun rotated and had spots, and that Jupiter was orbited by its own moons. Each discovery chipped away at the idea that Earth was the center of a flawless and unchanging universe. But there was still one more observation, one that would provide clear geometric confirmation of heliocentrism, the theory proposed by Nicolaus Copernicus decades earlier. This observation involved the planet Venus, and the fact that it, like the moon, goes through phases. To understand why this was important, we must look at the competing models of the universe at the time. In the Ptolemaic, or geocentric model, the Earth is fixed at the center of the cosmos. All planets and the Sun orbit around it, in complex paths, involving circles within circles known as epicycles. In this model, Venus orbits between the Earth and the Sun, therefore, it should only ever appear in certain positions relative to the Sun. According to Ptolemy, Venus should never be seen in a fully illuminated phase, like a full moon, because from Earth's perspective, Venus would always be positioned somewhere between us and the Sun. At most, it should appear as a crescent. But in the heliocentric model proposed by Copernicus, the planets, including Venus, orbit the Sun, not the Earth. From that perspective, Venus sometimes passes between Earth and the Sun, and sometimes it moves to the far side of the Sun. When Venus is between Earth and the Sun, we should see a crescent phase. But when Venus is on the opposite side of the Sun, we should see it nearly fully illuminated. These predictions were not philosophical, they were testable. If Venus showed a full range of phases, including nearly full, that would directly contradict the Ptolemaic system. And that is exactly what Galileo set out to observe. Using his improved telescope, Galileo began tracking Venus in the evening sky. He observed its size, its brightness, and most critically, its phase. How much of its disk was illuminated. He documented that Venus did not always appear the same. Sometimes it was a bright crescent, large in size. Sometimes it was smaller and nearly full. The change followed a predictable cycle. Let's explain what Galileo saw in modern terms. When Venus is closest to Earth, it appears as a crescent. As it moves around the Sun, its illuminated portion grows. When Venus is on the far side of the Sun, it appears nearly full, but also smaller because it is farther away. This sequence of changing phases matches exactly what is predicted by the heliocentric model, and most importantly, it cannot be explained by the Ptolemaic system. That system had no geometric mechanism to allow Venus to show a full phase, because Venus was thought to always stay between Earth and the Sun, along an epicycle. In that configuration, the Sun would always backlight Venus, preventing it from ever appearing fully illuminated. Galileo published his findings on the phases of Venus in 1611, confirming what Copernicus had theorized more than 60 years earlier. But Galileo was not merely confirming a theory, he was transforming astronomy from a set of calculations into a physical science, grounded in observation. With his telescope, he had now confirmed that the Moon had terrain, that Jupiter had orbiting moons, that the Sun rotated and had imperfection, and that Venus orbited the Sun, not the Earth. These four observations formed a coherent case, not based on authority, but on direct empirical data. And the case was clear. The heliocentric model was not just a theoretical convenience, it was the structure of reality. This conclusion, however, came at a cost. By this time, the Catholic Church had already begun to grow uneasy with Galileo's findings. The Copernican model conflicted with scriptural passages that described the Earth as immobile and the heavens in motion. Galileo's discoveries, particularly those confirming heliocentrism, were now seen as not just scientific challenges but theological threats. Still, Galileo persisted. He knew the evidence was undeniable. The phases of Venus were observable through any properly constructed telescope. They were reproducible, geometric, and independent of interpretation. This made them powerful and dangerous. Let us understand the geometry behind this. In the heliocentric system, the motion of Venus around the Sun creates elongations, where Venus appears farthest from the Sun in the sky, and conjunctions, where Venus is closest to the Sun from our perspective. When Venus is in inferior conjunction, it passes between Earth and the Sun and appears as a thin crescent. When it moves to superior conjunction behind the Sun, it becomes nearly full. Galileo tracked these changes and documented them with drawings. He noted the change in apparent diameter, how Venus appears larger when closer and smaller when farther away. He also noted the changes in brightness which corresponded not just to distance but to the illuminated fraction of the planet's disk. This was a breakthrough. For the first time, a planet had been observed showing phases, just like the Moon. It implied that planets reflect sunlight, and their appearances change based on their position relative to Earth and the Sun. This observation wasn't just a point of data, it was a window into the kinematics of the solar system. It confirmed that the planets were real, physical objects, not perfect lights or embedded spheres. It also introduced a new concept to astronomy, the observer's frame of reference. What we see depends on where we are in the system. This idea would later influence thinkers like Newton, and centuries later, Einstein. Galileo's observation of Venus's phases also allowed for a new kind of astronomical prediction. He could now forecast when Venus would appear as a crescent, when it would be bright or dim, and how its apparent size would change, all with mathematical regularity. This marked the beginning of a predictive astronomy, based not on epicycles and guesswork, but on physical models, geometry, and real data. The beauty of the heliocentric model was that it made fewer assumptions and explained more observation, and the phases of Venus were one of its strongest pieces of supporting evidence. Galileo didn't just observe the phases, he used them as a logical instrument. He showed that they made sense only if Venus orbited the Sun. This meant one thing, clearly and irrevocably: the Ptolemaic system was wrong, and this conclusion spread rapidly. Other astronomers across Europe began confirming the phases of Venus with their own telescopes. Galileo's observations were not secret knowledge, they were testable claims, open to replication. This was a hallmark of modern science, the idea that a claim is valid not because of who says it, but because anyone can verify it. By 1611, Galileo Galilei had already redefined observational astronomy. He had revealed mountains on the Moon, confirmed moons orbiting Jupiter, observed the phases of Venus, and tracked sunspots across the rotating face of the Sun. Each discovery had widened the known structure of the cosmos. Now, he turned his telescope toward another celestial body, one that had fascinated astronomers for centuries, but never revealed its full secrets. That planet was Saturn. To the naked eye, Saturn appeared as a bright, slow-moving star in the night sky. But when Galileo pointed his telescope toward it, he saw something entirely unexpected, something that did not fit into any known celestial category. He described Saturn as having strange appendages. In his own words, he wrote that Saturn appeared triple-bodied, a large central sphere with two smaller bodies on either side. To Galileo's eyes, it looked like the planet had ears. We now know that what Galileo was seeing were Saturn's rings, the most iconic planetary feature in our solar system. But his telescope, while revolutionary, did not have the optical resolution to reveal the rings as such. Instead of a flat circular disk, Galileo saw two symmetrical lobes on either side of the planet. He was puzzled. Were these moons? Were they physical extensions of the planet? Were they orbiting structures? The image was stable. Night after night, the ears remained in place, but they didn't behave like the Galilean moons of Jupiter, which changed position regularly. Galileo observed that these structures were fixed in position relative to the planet. They did not orbit. They did not shift side to side. They appeared as permanent attachments, solid and mysterious. In 1610, when he first described the appearance, Galileo wrote, "Saturn is not a single star, but is composed of three which almost touch one another, and never change nor move with respect to one another." To modern readers, this is a fascinating example of the limits of observation in early science. Galileo had the curiosity and the instrument, but not yet resolving power to see Saturn clearly. Still, he did not invent explanations. He documented what he saw and left the interpretation open. Over the next few years, Galileo continued to observe Saturn, but then something strange happened. In 1614, the ears disappeared. Saturn now appeared as a single, spherical body. The appendages were gone. This was deeply confusing. Had he made a mistake? Were the structures illusions? Had Saturn changed? We now know exactly what happened. Saturn's rings are tilted relative to the plane of its orbit. As the planet moves along its orbital path, the angle at which we observe the rings from Earth changes. Every 14 to 15 years, the rings reach a point where they are seen edge-on, and from Earth, they become nearly invisible. Their thickness is so small compared to their diameter that they vanish from view. In 1614, Galileo happened to be observing Saturn during such a moment. The rings were still there, but they were aligned in such a way that his telescope, with its limited resolution, could no longer detect them. Later, as the years passed and Saturn's orientation changed, the ears reappeared. Galileo was astonished. This time, the structures seemed elongated, less spherical than before. He speculated that Saturn might be a mutable body, one whose shape changed over time. He recorded his confusion with honesty. What was once seen as three is now but one. How to explain this phenomenon? I do not yet know. This moment of not knowing speaks volumes about Galileo's approach to science. He did not fabricate a theory to fit his expectations. He admitted uncertainty. He continued observing, and he left a record of what the telescope could, and could not, resolve. This was one of Galileo's most important contributions, not a discovery in itself, but a lesson in methodology. He demonstrated how a scientist behaves in the presence of incomplete data, with humility, with rigor, with patience. Today, we understand Saturn's rings as a complex system of icy particles, ranging in size from dust grains to small boulders. They orbit the planet in a thin, flat plane, governed by the laws of gravity and orbital resonance. These rings were not clearly resolved until Christian Huygens, using a much more advanced telescope in 1655, proposed that Saturn was surrounded by a thin, flat ring, which touches it nowhere and is inclined to the ecliptic. But it was Galileo who first observed the rings, even if he couldn't yet interpret them as such. His drawings, published in later editions of his works, show Saturn with distinct side lobes, clearly the first documented sighting of planetary rings in human history. This episode also revealed something crucial about the telescope. As powerful as it was, it had limitations. Galileo's early instruments had narrow fields of view, low light gathering capacity, and significant optical aberration. Straight lines curved near the edges, bright objects bled into halos, fine detail was difficult to resolve. Saturn, with its distant orbit and subtle structures, was a test case for the limitations of early optical science. Galileo's confusion was not a failure, it was an opportunity, one that underscored the need for better lenses, improved methods and deeper patience. His work on Saturn reminded the world that science does not always provide immediate answers. Sometimes it provides only patterns without explanation. Sometimes it challenges the observer to keep looking, even when meaning is not yet clear. The limits of early telescopy also raised a larger question for Galileo. What if our instruments are always partial? What if reality is more detailed than our tools can show? And more importantly, how do we trust what we see when our instruments introduce distortion? Galileo responded by doing what every great scientist does. He calibrated his tools. He replicated observations. He shared data so others could compare results. His observations of Saturn were imperfect, but they were honest, and they were the first step toward one of the most iconic astronomical discoveries ever made. He had glimpsed the mystery of the rings, and even without fully understanding them, he documented what he could, and pushed the boundaries of instrument-based observation. This marked a transition in science, from the naked eye to the enhanced eye, from what the body could see to what the instrument could reveal. This idea that our tools define what we know would go on to shape the development of microscopy, spectroscopy, electromagnetism, and eventually quantum physics. Galileo was there at the beginning. With his telescope aimed at Saturn, he realized something profound, that the universe might always be just out of focus, waiting for better tools, better minds, and better questions. He did not know that Saturn had rings. He did not see the particles, the structure, the divisions, but he saw enough to ask. And that is what science is built on. Not answers, but questions powered by observation. Galileo's notes on Saturn would eventually help astronomers like Huygens and later Cassini to decode the planet's true structure. But even in confusion, Galileo provided something invaluable: a method, a record, a challenge, to look again, to build better lenses, to trust the eye, but verify with reason. And that lesson, born from the blurred rings of Saturn, has guided every scientist since. When Galileo Galilei first aimed his telescope at the stars, he was not looking to measure their distance or to calculate their mass. He was simply trying to see more clearly, and what he found would trigger a fundamental shift in how humanity understood the scale of the universe. In the early 1600s, stars were widely believed to be fixed to a great celestial sphere, a vast, invisible dome that rotated around the Earth once every 24 hours. In the Ptolemaic system, the stars were thought to lie just beyond the orbit of Saturn, forming a firm boundary to the cosmos. Their brightness and position were taken as constant, but Galileo's telescope revealed something far more intricate. When he pointed his lens at sections of the night sky, especially those along the band of the Milky Way, he discovered that what the unaided eye perceived as a pale, luminous blur was, in fact, composed of countless individual stars. This was not metaphor. It was measurable. Galileo carefully described how regions that appeared cloudy or foggy were actually densely populated star fields, their individual lights too faint or too close together to be resolved without magnification. He wrote, "The galaxy is nothing but a mass of innumerable stars planted together in clusters." This realization was profound. It implied that the universe extended far beyond the solar system, not just in size but in quantity. If the Milky Way contained countless stars invisible to the naked eye, then the cosmos was not bounded by a crystalline sphere. It was open, layered, and populated on a scale previously unimaginable. Galileo made detailed sketches of these regions. In some areas, he mapped out hundreds of stars per square degree of sky. He noted the difference in brightness, spacing, and density, and he began to suspect that many of the stars visible through the telescope were at vastly different distances. This was a break from classical thinking, which held that all stars were essentially equidistant from Earth. He did not yet have a way to measure stellar parallax, the tiny shift in a star's position due to Earth's orbit around the Sun, but his observations hinted at depth. Some stars appeared brighter and larger, others were fainter and smaller. While Galileo knew this could be influenced by atmospheric effects or telescope limitations, he cautiously proposed that stars might vary in both size and distance. He also turned his telescope toward known constellations patterns that had been charted by astronomers for centuries. What he found was that between the prominent stars of these constellations were many more that were invisible to the unaided eye. The shape of the constellation remained, but now it was embedded within a sea of unseen stars. The sky was no longer a canvas of isolated lights. It was a volume filled with stellar objects layered in distance, brightness, and position. This idea that the stars were scattered throughout three-dimensional space, not fixed on a two-dimensional sphere, was a revolutionary shift. It turned astronomy into a question not just of motion but of structure. Where were the stars? How far away were they? Were they like the Sun? Galileo did not have the answers, but he had the right questions. His observations laid the groundwork for a conceptual leap, from a finite Earth-centered universe to a cosmic expanse whose dimensions could not be measured with existing tools. He also proposed for the first time a possible nature of stars. He suggested that stars might be distant suns, self-luminous bodies, scattered throughout space. This idea was not entirely new, but Galileo gave it observational weight. By comparing the brightness and disk size of stars seen through his telescope, he argued that their luminosity might be due to their own light, not reflected light like the planets. In this view, the Sun was no longer unique. It was simply the closest example of a stellar object. This was a radical notion. If stars were suns, then perhaps other systems existed, complete with planets, and perhaps even forms of life. While Galileo never directly claimed the existence of exoplanets, the implications of his observations were clear. The cosmos was not a closed, Earth-focused hierarchy. It was a field, a vast collection of light-emitting bodies scattered through space, and humanity was not at its center. Galileo's maps of the sky grew increasingly detailed. He drew clusters, double stars, and star chains. He sketched globular formations, what we now call star clusters, in which hundreds or thousands of stars appeared densely packed. These sketches helped future astronomers identify and catalogue celestial structures with precision. Among his most important observations was the realization that increased magnification always revealed more stars. No matter how small or dark a region of sky seemed, a better telescope would uncover new layers. This suggested a kind of cosmic infinitude. The stars were not limited in number, they extended beyond the reach of any eye or lens. Galileo's conclusion was both philosophical and scientific. The universe is not built to human scale. This realization had psychological consequences. If the cosmos was vast and unbounded, then the traditional theological picture of the universe as a space built for Earth, bounded by stars, no longer held. Instead, Galileo presented a vision of the universe as natural, self-organizing, and profoundly indifferent to human centrality. It was not a hostile vision, but it was humbling, and that humility, the recognition of scale, became a cornerstone of modern astronomy. Galileo's writings on the stars are calm, precise, and filled with wonder. He does not speculate wildly, he does not leap beyond the evidence, but he allows the data to suggest a reality far larger than previously imagined. For example, he noted that even in the smallest visible areas of the sky, the density of stars was enormous. He speculated that the number of stars might be effectively limitless, and that their distribution was governed not by symmetry or design, but by natural processes yet to be understood. This raised a deeper question. Was the Milky Way just one part of a larger system? Could there be other collections of stars, other galaxies far beyond the reach of his telescope? Galileo did not have the optical tools to answer this, but his writings allowed that the cosmos might extend without boundary. In this way, Galileo introduced what we now call the cosmological perspective, a view of the universe in which the Earth is not central, the stars are not fixed, and the structure of the cosmos must be discovered, not assumed. It was this perspective that led, centuries later, to the discovery of other galaxies, nebulae, and the expansion of space itself. But it began here, with a telescope, a sketch pad, and a man willing to say, "I see more than I thought was there." Galileo's star observations did not provide immediate models or measurements. They provided awareness, but awareness became the framework for further inquiry, for building larger telescopes, and for asking bigger questions. Even today, astronomers use the same fundamental approach: look deeper, record carefully, and never assume the sky is empty. Galileo taught us that even the darkness between stars is full of light, waiting to be resolved, and in doing so, he helped reshape not just astronomy, but the human imagination. In the year 1632, Galileo Galilei published the most ambitious and controversial work of his life. It was not a collection of observations, it was not a technical manual, it was a dialogue, a structured, reasoned conversation in which arguments were tested, challenged, and laid bare for public scrutiny. The title of the book was Dialogue Concerning the Two Chief World Systems. Its purpose was clear: to present and compare the geocentric model of Ptolemy and Aristotle with the heliocentric model of Copernicus. But behind that neutral framing was something far more pointed. Galileo was making his most forceful and public case for heliocentrism. This was a dangerous choice. By the early 17th century, the Roman Catholic Church had declared the Copernican model to be formally heretical, because it contradicted certain scriptural passages that described a fixed Earth and a moving sun. In 1616, Galileo had been privately warned by church officials not to hold or defend heliocentrism. For years he obeyed, at least publicly, but now, with the support of Pope Urban VIII, and under the premise of impartial discussion, Galileo returned to the debate. The dialogue was structured not as a lecture, but as a 4-day conversation among 3 fictional characters: Salviati, the voice of reason and science. He represents Galileo's own views and supports Copernican theory. Simplicio, a sincere but rigid follower of Aristotle and Ptolemy. He argues for the traditional geocentric view. Sagredo, an intelligent layman, curious and open-minded. He represents the educated reader, asking questions and weighing both sides. This format allowed Galileo to do something subtle. He could present controversial arguments without asserting them directly. He let his characters explore evidence, logic, and experiment, letting the reader come to conclusions themselves. But it was clear, Salviati's arguments were better supported, better reasoned, and ultimately more persuasive. The dialogue spans topics such as the motion of the Earth and its consequences, the behavior of falling bodies, tidal theory, the structure of the heavens, the nature of celestial spheres, the appearance of stars and their distance, the phases of Venus and the motion of Jupiter's moons. Each topic is examined with care, depth, and clarity. One of Galileo's key rhetorical strategies was to show how observations align with the heliocentric model. He did not claim certainty, but plausibility grounded in evidence. He asked, if Earth rotates, why do we not feel it? If Earth moves around the Sun, what observable effects should we expect? If we look through the telescope, what does it reveal about our place in space? He used analogy, data, and real measurements to support his claims. For instance, he explained how the apparent retrograde motion of planets, their occasional backward loop in the sky, was naturally explained by Earth's own movement. In the geocentric model, retrograde motion required complex epicycles, but in the heliocentric model, it was a simple effect of parallax, the perspective shift caused by Earth overtaking another planet in its orbit. Galileo also addressed stellar parallax, the small shift in a star's position caused by Earth's orbit. Critics of heliocentrism argued that if Earth really moved, we should see stars shifting in the sky. Galileo responded that the stars are much farther away than previously believed. The parallax was real, but too small to detect with the instruments of the time. He was right. Stellar parallax was not successfully measured until the 19th century, using far more precise telescopes. Galileo had anticipated the result, based on geometry and reason. Another major theme of the dialogue was motion on a moving Earth. Critics had argued that if Earth rotates, a stone dropped from a tower should fall behind as the tower moves eastward. Galileo explained that all objects on Earth share its motion. A ball dropped from the mast of a moving ship still lands at the base of the mast, not behind it. This principle would later become part of Newton's laws of motion, but Galileo saw it intuitively. He introduced the concept of inertia, the idea that motion continues unless something interrupts it. This was a break from Aristotelian physics, which claimed that constant motion required constant force. Galileo showed that uniform motion was natural, and that acceleration required explanation, not motion itself. Another chapter of the dialogue explored the nature of tides. Galileo proposed a theory linking tides to Earth's rotation and orbit. He was wrong about the mechanics. Tides are caused primarily by the moon's gravitational pull. But the significance was this: he was trying to explain natural phenomena with physical motion, not divine influence or mystical properties. He was applying reason, not relying on tradition. Throughout the dialogue, Galileo constantly returned one theme: the telescope has changed what we know. He reminded readers that they had seen the phases of Venus, the moons of Jupiter, the spots on the sun, and the structure of the Milky Way. These were not philosophical theories, they were observations, and any theory that could not explain them, such as the Ptolemaic model, was no longer acceptable. The dialogue also revealed Galileo's literary skill. The characters were lively, the tone was engaging, the arguments were detailed but clear. He did not shout, he reasoned, he asked questions, invited scrutiny, and allowed the facts to speak. But the most controversial aspect of the dialogue was the character of Simplicio. He was not a caricature, he was sincere, but he was also wrong, frequently. And in the final pages of the book, Simplicio repeats a theological argument that Pope Urban VIII had personally shared with Galileo during an earlier audience, that God, in his omnipotence, could make the universe appear any way he wished, and that human reasoning could not limit divine power. By placing this argument in the mouth of Simplicio, Galileo was seen by some as mocking the Pope. It was not necessarily his intention, but in the political and religious climate of the time, the message was dangerous. The dialogue was a bestseller. It was published in Florence and distributed across Europe. It was widely praised by scientists and scholars, and it reignited debate on the structure of the cosmos. But it also triggered a response from the Roman Inquisition. In 1633, less than a year after its publication, Galileo was summoned to Rome. There he faced a formal charge of heresy. Church authorities argued that he had violated the instructions given in 16 specifically, that he had held and defended the Copernican model as physical truth. Galileo maintained that the dialogue merely presented arguments, not conclusions, that the Church saw through the framing, the force of Galileo's reasoning, the clarity of Salviati's voice, and the ridicule of geocentric ideas were too strong to ignore. In the eyes of the Inquisition, Galileo had crossed the line. He was tried, he was interrogated, he was threatened with torture. Eventually, Galileo was forced to recant. He formally stated that he no longer held the belief that the Earth moved. Legend has it that as he rose from his knees, he whispered, "I si muove," and yet it moves. There is no proof he said it, but history remembers the phrase because it captures the spirit of Galileo's work. Truth does not yield to pressure. It remains. And even under threat, Galileo had built a case that would shape science forever. The dialogue was banned. Galileo was sentenced to house arrest for the rest of his life. But his ideas continued to circulate. Within decades, they would be refined, confirmed, and expanded by thinkers like Kepler, Newton, and Huygens. The dialogue remains one of the most important scientific works in history, not because of what it claimed, but because of how it argued. It used reason. It used evidence. It used dialogue. It invited people not just to believe, but to think. And in doing so, it taught a generation how to ask the right questions. Galileo's case for Copernicanism was not only about the sun and earth, it was about the role of observation, the power of logic, and the courage to challenge orthodoxy. By the year 1633, Galileo Galilei was no longer free. He had been tried by the Roman Inquisition, forced to recant his belief in heliocentrism, and sentenced to house arrest for the remainder of his life. At the age of 69, his movements were restricted. He was forbidden from writing about astronomy. But Galileo did not stop working. In the quiet of his home in Arcetri, near Florence, he began his final and perhaps most enduring scientific project. This time, he turned away from the skies. He turned toward the physics of motion, the laws that govern falling objects, swinging pendulums, and the behavior of materials under stress. The result was a book called Discourses and Mathematical Demonstrations relating to two new sciences, published in 1638. It was Galileo's final major work, completed while under surveillance and smuggled to the Netherlands for publication. In it, he laid the foundation for what would later become classical mechanics. The book is structured as a dialogue, much like his earlier dialogue concerning the two chief world systems. Three characters, Salviati, Sagredo, and Simplio, return once again to explore the principles of nature through discussion, thought experiments, and logical derivation. This time, however, the topics are kinematics and material science. The first new science discussed in the book is the strength of materials. Galileo asks, how does the size of a structure affect its ability to bear weight? This question may seem simple, but it touches on deep principles of geometry and physics. Galileo shows that as an object increases in size, its volume grows faster than its surface area. This leads to important consequences. For example, a beam that supports its own weight, at a small size, will break under its own weight if scaled up proportionally. Galileo mathematically demonstrates this relationship, foreshadowing what we now call scaling laws. He shows that the strength of a beam is proportional to its cross-sectional area, while its weight is proportional to its volume. If a beam's width and height are both doubled, its weight increases by a factor of 8, but its strength increases only by a factor of 4. This means that large structures must be shaped differently from small ones if they are to remain stable. This insight helped guide future engineers and architects in the design of bridges, domes, and towers. Galileo also discusses how materials behave under stress. He explains the concept of tensile strength, the amount of force a material can withstand when stretched, and compressive strength, which refers to resistance to crushing. Though he did not have the modern vocabulary equipment, he effectively laid the groundwork for the field of material mechanics. The second new science in the book is kinematics, the mathematical study of motion. Here, Galileo makes his greatest contributions to modern physics. He begins by asking, how do objects fall? For centuries it was believed, following Aristotle, that heavier objects fall faster than lighter ones. Galileo refuted this by proposing that in the absence of air resistance, all objects fall at the same rate. He describes an idealized experiment: two spheres of different weights dropped from the same height. If there is no interference from the air, they hit the ground at the same time. This idea was radical. It replaced qualitative speculation with quantitative prediction. Galileo then introduces the concept of uniform acceleration. He proposes that a freely falling object does not fall at a constant speed, but instead gains equal amounts of velocity in equal intervals of time. This means the object is accelerating at a constant rate. He expresses this in mathematical form. Let the distance an object falls be denoted by s, and the time it takes by t. Galileo discovered that the distance fallen is proportional to the square of the time. In modern terms, we write s equals 1/2 times g times t squared, where this is the distance fallen, g is the constant acceleration due to gravity, t is time. This was a groundbreaking insight. It showed that motion could be described with precise mathematical relationships, not just verbal descriptions. Galileo didn't have the exact value for g, the acceleration due to gravity, but he proved that the relationship between distance and time squared held consistently. To test his theory, Galileo constructed an ingenious experiment. He built an inclined plane, a long, smooth ramp at a shallow angle, and rolled a small ball down it. This slowed the acceleration enough that he could measure time intervals using a water clock, timing how much water flowed out of a container during each portion of the ball's descent. He found that the distances the ball traveled increased in proportion to the sec of the elapsed time. If t equals 1, the distance is 1 unit. If t equals 2, the distance is 4 units. If t equals 3, the distance is 9 units. This confirmed the uniform acceleration model. Galileo also derived a formula for final velocity. He showed that the speed an object reaches after falling is proportional to the square root of the distance fallen. In modern terms, v squared equals 2 times g times s, where v is the final velocity, g is the gravitational acceleration, s is the distance fallen. Again, Galileo did not write the equations in this modern notation, but the relationships were present in his geometric arguments. He used proportions, diagrams, and rigorous logic to reach conclusions that would later be rewritten in algebraic form. One of his most insightful conclusions involved projectile motion. Galileo showed that the path of a projectile, such as a cannonball, is a parabola. This was a breakthrough in understanding how vertical and horizontal motions combine. He demonstrated that horizontal motion remains constant, while vertical motion is uniformly accelerated. Together, they form a curved trajectory. This principle, now fundamental in physics, allowed future scientists and engineers to predict the motion of objects in 2 dimensions with remarkable accuracy. Galileo's approach in 2 new sciences was systematic. He used thought experiments to isolate principles, real experiments to gather data, geometrical proofs to demonstrate consistency, dialogue to make the material accessible. This method was a prototype for modern scientific inquiry. In addition to physics, Galileo also discussed problems of infinite sequences and ratios. He explored paradoxes involving infinite sets, such as the fact that there are as many square numbers as whole numbers, even though square numbers are only a subset. This anticipated ideas in set theory and mathematics of infinity that would be formalized centuries later. What makes 2 new sciences so remarkable is its blend of mathematical rigor, physical insight, and didactic clarity. Galileo wasn't just reporting results, he was teaching a way of thinking, a way of modeling the world with logic and measurement, a way of treating physical reality as something to be understood, predicted, and verified. He did this without access to calculus, vectors, or modern instruments. He worked with simple tools, careful timing, and brilliant reasoning. His work directly influenced Isaac Newton, who later cited Galileo as a foundational figure in his Principia Mathematica. Newton's laws of motion, the law of universal gravitation, and the mathematical treatment of force all build upon the ideas Galileo introduced. In this sense, 2 New Sciences is not just a final book, it is a bridge between medieval physics and modern science. Galileo's ability to isolate variables, to imagine idealized systems and then test them as closely as possible in the real world, changed the method of scientific investigation. It introduced what we now call the scientific method, not trial and error, not speculation, but structured, testable hypotheses grounded in repeatable observations. Despite his house arrest, Galileo continued to correspond with scientists across Europe. He shared manuscripts, reviewed others' findings, and remained intellectually active until his death in 1642. Though his body was confined, his ideas were not. They traveled through letters, copies, and minds eager to learn. By the time he died, Galileo had transformed 3 fields: astronomy by proving the heavens were not immutable, physics by introducing quantitative laws of motion, methodology by modeling a new way of discovering truth, and he did so under constraint, with vision undimmed. 2 New Sciences is a quiet masterpiece. It contains no provocations, no theological conflicts, no grand claims. It is simply a long, thoughtful, carefully reasoned exploration of how things move and how they break, and in doing so, it reshaped human understanding of the material world. Galileo showed that nature is not governed by arbitrary rules. It is governed by patterns, ratios, and relationships waiting to be discovered by those who observe with care and think with clarity. Galileo Galilei did not invent the telescope. He did not discover gravity. He did not complete the laws of motion. But what he did change, permanently, was the nature of knowing itself. He redefined how humans seek truth, how evidence is measured, and how logic challenges authority. By the time he died in 1642, Galileo had left behind more than instruments and manuscripts. He had introduced a system of thought, a process, a new relationship between observation, reason, and reality. This chapter is not about a specific discovery. It is about how Galileo transformed the foundation of science, and what that means even today. Before Galileo, knowledge was structured around authority. The writings of Aristotle, the teachings of the Church, the consensus of ancient philosophers. Truth was determined by consistency with tradition. But Galileo shifted the axis of knowledge. He placed it on something else, something that could be verified, tested, and repeated: experience. He believed that nature could speak for itself, and he believed our role was not to defend inherited beliefs, but to ask, what can we observe? This did not mean rejecting all tradition. It meant checking every claim against evidence. It meant that no idea, however old, however sacred, was exempt from examination. This was not merely a scientific shift. It was an epistemological revolution. Galileo introduced a hierarchy of truth. First, direct observation. Second, mathematical consistency. Third, logical inference. And last, tradition. Valid only if supported by the first three. This structure reversed the medieval order. It empowered individuals to reason for themselves, provided they followed a rigorous method. Galilei's method was simple in principle. Start with a phenomenon. Ask a measurable question. Isolate variables. Design experiments or observations. Quantify outcomes. Use mathematics to describe the results. Today, this process is known as the scientific method, but in Galilei's time it was revolutionary. He applied it across domains: astronomy, physics, materials, and even motion. He showed that consistent reasoning could link what we see with how things work. Importantly, he also introduced a concept that was philosophical at its core, that nature is lawful. It does not act by whim, but by principle. It is not chaotic, but patterned. And those patterns can be written in the language of mathematics. In a famous passage, Galileo wrote, "Philosophy is written in that great book which ever lies before our eyes. I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. It is written in mathematical language." To him, mathematics was not an abstraction. It was the grammar of reality. This idea set the stage for the work of Isaac Newton, who would go on to express gravity, inertia, and motion in mathematical laws. But it was Galileo who demonstrated that mathematics could describe real motion: rolling balls, swinging pendulums, falling weights, not just abstract shapes. He connected number to nature. His work also changed how instruments were viewed. Before Galileo, instruments were tools of navigation or warfare, practical but not epistemological. Galileo elevated them to tools of discovery. The telescope was not just for sailors, it was a device for seeing what the eye alone could not. This introduced a new idea that instruments extend the senses, and if they are calibrated, repeatable, and carefully interpreted, they can tell us truths beyond what we were biologically designed to perceive. Today, we use particle detectors, electron microscopes, gravitational wave observatories, all are descendants of Galileo's telescope. There is also Galileo's legacy in language. He was a gifted communicator. He wrote not only in Latin, but in Italian, so that educated readers outside the clergy could follow his arguments. This broke the barrier between expert and citizen. It seeded a culture in which scientific reasoning was not just elite knowledge, but public discourse. He wrote as a teacher, not a preacher. He used dialogue, analogy, and vivid examples. He did not rely on authority. He built trust by showing the steps of his reasoning. In doing so, he modeled a new kind of thinker, not the oracle, but the transparent investigator. Even in conflict, Galileo remained committed to reason over rhetoric. He did not attack religion. He attacked bad arguments. He distinguished between the spiritual and the natural, insisting that understanding one did not diminish the other. In fact, he believed that science could enhance reverence by revealing the structure, subtlety, and scale of creation. But the church at the time did not agree. To preserve doctrinal authority, it rejected observational reality. It silenced the data. It criminalized interpretation. And in doing so, it made Galileo into a symbol of conflict between dogma and evidence, power and inquiry, certainty and curiosity. This symbolic role has endured. Even now, centuries later, Galileo stands as a figure in debates over censorship, over freedom of thought, over the right to question. His trial in 1633 remains one of history's defining moments for intellectual independence. But Galileo's legacy is not about the fiber, it is about the foundation he laid. He left us three critical pillars that still support modern science. Empiricism, knowledge begins with observation. Quantification, math reveals consistent relationships in nature. Method, reasoned procedure, protects against bias and error. These ideas are embedded in every field of science today. Whether studying cells, galaxies, or subatomic particles, we still follow Galileo's template: observe, measure, model. Galileo also helped restore a forgotten idea from ancient Greece: that truth is not given, it is found, and it must be tested, not assumed. This put humanity on a path away from myth and toward mechanism, from magical causality to lawful processes, from superstition to structure. What makes his legacy even more remarkable is the breadth of his influence. In astronomy, he overturned the static cosmos. In physics, he introduced time, motion, and inertia as measurable entities. In engineering, he He laid groundwork for materials and scaling. In methodology, he gave us the blueprint for systematic inquiry. He touched each of the core domains of modern science. Yet, Galileo was not a man of institutions. He worked largely alone, often at risk, often in defiance. He had no formal lab, no staff, and no legal protection. All he had was a telescope, a notebook, and a mind unwilling to be quiet. And that may be his greatest legacy of all. He showed that knowledge does not require permission. It requires discipline. It requires clarity. And it requires the courage to say, "This is what I see." In 1694, long after his death, the Church placed Galileo's books back on the list of forbidden texts. It would take centuries before his name was cleared. In 1992, Pope John Paul II formally acknowledged the Church's error. He praised Galileo's faith and intellect, and called the trial a tragic mutual misunderstanding. But the world had already moved on. By then, we had telescopes in orbit, rovers on Mars, satellites measuring cosmic background radiation. Each of those achievements followed a path that Galileo had helped clear, not by reaching the stars himself, but by showing us that they were not perfect, not eternal, and not unreachable. They were places, objects, subjects of inquiry. Galileo's universe was not smaller than the old one. It was infinitely larger and far more interesting, because now it was open to question, to wonder, to understand. We remember Galileo not because he had all the answers, but because he asked better questions, because he trusted what he could measure, even when others denied it, because he believed that truth, once seen, could not be unseen. Galileo Galilei did not live to see the revolution he had begun. He died in 1642, under house arrest, blind in both eyes, and cut off from the academic world he once stirred. But even in isolation, his work had already ignited a transformation. A scientific fire had started, and it would not be extinguished. This chapter is not about Galileo alone. It is about the inheritors of his vision, those who read his books, learned from his methods, expanded his questions, and turned scattered observations into universal laws. These are the minds who took Galileo's framework and built the scientific revolution. In the decades following his death, Galileo's ideas did not fade. They traveled. They reached the hands of mathematicians, philosophers, astronomers, and experimentalists across Europe. The telescope became standard scientific equipment. The idea of experiment-based science began to replace scholastic tradition. The principle of inertial motion spread from lecture halls to textbooks. One of the first and most prominent inheritors of Galileo's legacy was René Descartes. Though Descartes and Galileo never met, Descartes was deeply aware of Galileo's contributions, especially his mathematics of motion. Descartes helped lay the groundwork for analytical geometry, and he argued that physical processes should be explained in mechanistic terms. He viewed the universe as a system governed by laws, not divine will. This mechanical philosophy built directly on Galileo's insights. Where Galileo had used geometry, Descartes introduced coordinate systems, linking spatial position with equations. This approach would later become essential for formalizing motion. But Descartes did not rely on experiments the way Galileo did. He preferred deduction from first principles, using logic to build the cosmos. This marked a divergence, a branch in Galileo's legacy, one empirical, one rationalist. A second key inheritor was Christian Huygens of the Netherlands. Born in 1629 during the peak of Galileo's house arrest, Huygens became one of the most skilled physicists of the 17th century. He improved the design of telescopes, invented the pendulum clock, and extended Galileo's work on circular motion and centrifugal force. Huygens carefully studied the laws of pendulums, using them to regulate timekeeping. Where Galileo had first observed the isochronism of the pendulum, its near-constant swing period, Huygens mathematically derived the behavior using geometry and experimentation. He showed that the period of a simple pendulum depends only on its length and the gravitational constant, not on mass or amplitude. In words, the period is proportional to the square root of the length, divided by gravitational acceleration. This led to a new way of measuring time, more consistent than ever before. Huygens also explored impact physics, collisions and elastic bodies. He used Galileo's ideas about inertia and motion to define conservation principles, including what we now call momentum. His writings built a bridge between Galileo's intuitive mechanics and Newton's formal laws. Then came Robert Hooke, working in England. Hooke was an architect, astronomer, inventor, and philosopher. He admired Galileo deeply, and his famous micrographia built on the idea that instruments extend perception. Using the microscope, Hooke observed cells, plant structures, and insects in extraordinary detail. He shared Galileo's belief that small, careful observations could reveal universal truths. Hooke also formulated what is now called Hooke's law, that the force needed to extend or compress a spring is proportional to the distance it is stretched. This idea linking force and displacement paved the way for Newtonian dynamics. Though Hooke and Newton would later clash, Hooke's experimental spirit was undeniably Galilean. And then there was Isaac Newton, born in the very year Galileo died, 1642. Newton inherited not only Galileo's questions but his approach. He read two new sciences and studied Galileo's mathematical treatment of falling bodies and parabolic motion. But Newton had tools Galileo lacked: algebra, calculus, and a better understanding of gravity. In 1687, Newton published the Philosophiae Naturalis Principia Mathematica. In it, he stated the three laws of motion, each an evolution of Galileo's work. Let's recall them in simple TTS-friendly terms. An object in motion stays in motion in a straight line unless acted on by a force. This is Galileo's principle of inertia. Extended, the acceleration of an object is proportional to the net force acting on it, and inversely proportional to its mass. This formalizes motion. Force equals mass times acceleration. For every action, there is an equal and opposite reaction, an idea that unifies interaction between bodies. Newton also formulated the law of universal gravitation. He proposed that every mass attracts every other mass, with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. This was the first time terrestrial and celestial motion were described by the same equation. Where Galileo had shown that objects fall with equal acceleration, Newton explained why. Where Galileo had described the parabolic path of projectiles, Newton extended it to planetary orbits. He unified Galileo's terrestrial physics with Kepler's celestial mechanics. The result was a new framework, classical physics. But Newton himself credited Galileo. He acknowledged that Galileo's experimental techniques, mathematical insights, and observational rigor had cleared the path. Without Galileo's work, the Principia would not have been possible. Galileo's influence extended even further. In the late 17th and early 18th centuries, scientific societies flourished. The Royal Society in England, the Académie des Sciences in France, the Accademia del Cimento in Florence, founded by Galileo's followers. Each of these institutions was grounded in experimental science. They prioritized observation, measurement, reproducibility, peer discussion. This cultural shift was Galilean at its core. Scientists began to believe that truth was emergent from nature, not dictated by books or dogma. Laboratories became cathedrals of knowledge. Data became sacred. Experiments were published, scrutinized, repeated. Theory was no longer enough. It had to be tested. This movement spread across Europe. In Germany, Gottfried Wilhelm Leibniz pursued dynamics and energy conservation. In Italy, Giovanni Borelli extended mechanics to biological systems, modeling muscles and animal motion. In Denmark, Ole Rømer measured the speed of light using observations of Jupiter's moons, a method made possible by Galileo's telescopic discoveries. In every case, Galileo's fingerprints were present, not in name, but in method, not in citation, but in structure of thought. His idea that nature could be explained using experiments and mathematics had become the default. Even in fields Galileo never touched, like chemistry or biology, his principles took root. In chemistry, Antoine Lavoisier introduced quantitative balances and conservation laws. In biology, William Harvey studied circulation through systematic dissection and inference. Both followed Galileo's rule: do not assume, measure, explain. In the realm of astronomy, Galileo's discoveries fueled the next steps. His moons of Jupiter proved that not all motion centered on Earth. His phases of Venus confirmed heliocentrism. His sunspot observations revealed solar dynamics. Later, Halley, Laplace, and Herschel would expand our map of the solar system using this new framework. The revolution was not limited to science. Galileo's insistence on evidence over authority inspired philosophers like John Locke and David Hume. The Enlightenment thinkers embraced empirical reasoning and skepticism of traditional power. This spirit influenced revolutions, not just scientific, but political and intellectual. Galileo had shown that truth could challenge kings, councils, and creeds, that a telescope pointed upward could change what people believed downward on Earth. In education, Galileo's work reshaped curricula. The shift from scholasticism to empirical science began with the textbooks of the 17th century and accelerated through the 18th. Students learned to test ideas, not just memorize them. In short, the scientific revolution was not just a burst of discoveries, it was a change in mentality, a new way of knowing. And Galileo was its spark. His inheritors built observatories, drew orbits, timed pulses, recorded impact, measured pressure, and described thermodynamics. They turned telescopes to stars, clocks to atoms, and mathematics to nature, and behind it all they followed one lesson: that nature is readable, but only to those who are willing to look, question, measure. This inheritance continues today. In every lab notebook, every peer-reviewed paper, every numerical simulation, the Galilean method endures. Not because it is a relic, but because it works. It is how we found the electron, decoded DNA, mapped the cosmic microwave background, and built machines that compute. The scientific revolution did not end. It continues with each generation extending the work of those before. Galileo was not the first, nor the last. But he was the one who showed us that knowledge grows by confrontation with reality, not just reflection on belief. Galileo Galilei lived and worked in the 17th century. He had no electricity, no satellites, no atomic clocks or quantum theory. Yet today, 400 years later, his ideas are still deeply relevant, not just in physics classrooms or observatories, but in the wider cultural and political landscape of the 21st century. Why? Because Galileo was not just a scientist, he was a pioneer of a mindset, a way of thinking that remains essential in a world shaped by data, algorithms, misinformation, and artificial intelligence. In this chapter we ask, what does Galileo's legacy mean now? What can we learn from his methods in an age where we are overwhelmed, not by ignorance, but by too much information? And how do we defend truth in a world where facts themselves are often treated as opinions? Let's begin with one core principle of Galileo's method: empirical skepticism. Galileo did not trust authority blindly, not even his own. He demanded evidence, not vague belief, not confident statements, measurable, repeatable observations. This might sound obvious today, but consider the digital landscape most people live in. We are constantly exposed to headlines, claims, graphs, quotes, and statistics. But how often do we stop and ask, what is the source? Was this tested? Is it reproducible? Galileo's mindset tells us that confidence is not evidence. A belief, no matter how passionately held, does not become truth unless it can be tested. This is a lesson as crucial in public discourse as it is in physics. In his time, Galileo was accused of arrogance for trusting his telescope over ancient texts. Today, we face a similar dilemma, but in reverse. Many people believe the tools are flawed, the scientists biased, or the institutions corrupt. And in some cases, skepticism is justified, but Galileo teaches us that skepticism must be paired with method. Skepticism alone is not enough. We must follow it with investigation. When Galileo observed the moons of Jupiter, he did not stop at surprise. He repeated the observation, he documented it, drew it, timed it, and invited others to check it themselves. This is how trust in science is earned. Not through claims, but through transparency and reproducibility. Today we live in a world where misinformation can spread faster than truth. An image can go viral before anyone has a chance to ask if it's real. An AI-generated voice can sound more convincing than a human expert. And in this environment, the Galilean approach is more important than ever. We must ask, can this claim be tested? Is there data behind it? Has it been peer-reviewed? Are there alternative explanations? These questions are not just academic, they are a defense against manipulation. Galileo's trials remind us that truth is often unpopular at first. He was ridiculed, censored, and punished, not because he was wrong, but because he challenged established power. In today's world, whistleblowers, investigative journalists, and independent researchers can face similar backlash. Galileo's life shows us the moral courage required to speak truth to power, when that truth is grounded in observable fact. Another modern lesson from Galileo is his belief in open access to knowledge. He wrote in Italian so more people could understand. He used diagrams, thought experiments, and everyday examples to explain complex ideas. In an age where science is often locked behind paywalls, his commitment to public understanding remains a standard we should strive for. Scientific literacy is not just for scientists. In a world where our choices, vaccines, energy, privacy, climate policy depend on science, everyone must understand the basics of how science works. Not every detail, but enough to ask good questions. Enough to know that not all claims are equal, that a randomized controlled trial is stronger than anecdotal opinion, that correlation does not mean causation. Galileo also reminds us of the importance of humility and discovery. He did not start with the answers. He started with questions. He didn't claim certainty, he looked for patterns. And when the evidence contradicted expectation, he changed his mind. That is not weakness, it is intellectual honesty. In modern science, this takes the form of peer review, error bars, and statistical confidence. It's why scientists say the evidence suggests rather than we know for sure. And yet, in popular culture, this caution is sometimes seen as doubt or weakness. Galileo teaches us otherwise. Real knowledge is provisional, always subject to refinement, and that's what gives science its strength. Unlike dogma, science updates, it admits mistakes, it corrects over time. That's not a flaw. That is the mechanism of progress. Let's turn to technology. Today, we use instruments far more advanced than Galileo's telescope. We analyze DNA, scan the universe for dark matter, and simulate ecosystems on supercomputers. But these tools still depend on the same principle Galileo used. Measurement must be connected to theory. Without interpretation, a number is just noise, and without evidence, a theory is just imagination. Galileo's approach, pairing mathematical description with empirical data, remains the blueprint for scientific instrumentation today. Whether it's analyzing particles in the Large Hadron Collider or monitor climate change through satellite data, we are still doing what Galileo did, asking the universe questions and listening to its answers through careful measurement. Galileo also reminds us of a deeper issue, the difference between belief and understanding. You can believe the Earth revolves around the Sun, but can you explain why we have seasons, or how Galileo's observations of Venus proved heliocentrism? In a society where belief is often emphasized over comprehension, Galileo's insistence on understanding is a powerful reminder. He did not want blind followers, he wanted thinkers, people who asked, looked, tested, and reflected. This is the core of critical thinking, a skill essential in a world full of algorithms designed to feed us what we already believe. In a time of echo chambers, Galileo's curiosity stands as a model of mental independence. He was not trying to be right, he was trying to understand. Let's also talk about artificial intelligence. Today, machines can identify galaxies, predict protein folding, and even generate scientific hypotheses. But even the most advanced AI still follows rules set by human logic, and that logic is built on centuries of method, starting with Galileo. AI does not replace the scientific method, it accelerates it. But it also inherits its limits. Garbage in, garbage out. That's why critical oversight matters more than ever. We need human interpreters who understand not just what the data says, but what it does not say. And that's where Galileo's mindset helps. He reminds us to doubt elegantly, measure precisely, and always question assumptions. Finally, Galileo offers a warning. He believed in reason, but he was not naive about power. He knew that even overwhelming evidence could be ignored, denied, or punished. His trial was not about science, it was about control. Control over who had the right to define truth. That question remains with us today. When scientists are discredited for political convenience, when evidence is buried under noise, when data is distorted to suit agendas, we are reliving Galileo's struggle. And like Galileo, we need more than data. We need defenders of reason, not just in labs, but in classrooms, in journalism, in public discourse. Because truth is not self-sustaining, it must be maintained, defended, taught. Galileo teaches us that science is not just a body of knowledge, it is a culture, a way of thinking, a habit of mind. And that culture only survives if it is practiced. In that sense, Galileo is not just a historical figure, he is a role model. Not because he was perfect, but because he was rigorous. Because he was willing to follow a question wherever it led, even if it led into danger. So what does Galileo mean today? He means that truth is discoverable. That method matters. That belief must bow to observation. That questions are sacred, and that science is not a faith, it is a discipline. A discipline of doubt, of measurement, and of careful thought. If we hold to that, we honor his legacy, not by building monuments, but by thinking like he did. Looking up, looking close, looking clearly. Why do we remember Galileo? It's not because he built the first telescope, nor because he dropped spheres from towers or charted the phases of Venus. We remember Galileo because he changed something deeper. He changed our relationship with truth. He taught us that knowledge is not inherited, it is discovered, and it must be earned through observation, reasoning, and courage. As we conclude this series, we pause not to honor a biography, but to consider a legacy. Galileo's life was not just a sequence of discoveries, it was a model of how to ask questions and how to live with the consequences of seeking answers. Let's begin where he began, with doubt. Galileo doubted what others accepted. He doubted Aristotle's physics, Ptolemy's cosmology, and even long-standing religious interpretations of the heavens. But his doubt was not cynical. It was structured. He didn't tear things down just to challenge them. He replaced assumptions with experiments, replaced belief with measurement. That is the first reason he still matters. In a world full of conflicting voices on science, politics, health, and technology, Galileo reminds us that doubt must be disciplined. Skepticism without method is just noise, but skepticism with evidence becomes science. Galileo also reminds us that science is not just about answers, it's about process. When he rolled balls down inclined planes or observed the moons of Jupiter, he wasn't seeking applause, he was testing reality. This mindset, the idea that truth is testable, has become the cornerstone of modern knowledge. From medicine to climate science to particle physics, we are still using Galileo's playbook. Observe, hypothesize, test, revise. He showed that knowledge is not what we're told, it's what we can demonstrate. This principle protects science from opinion. It gives science structure, and it gives it resilience. Even when challenged, the method remains. But Galileo's influence didn't stop at science. He also reshaped how we communicate ideas. He wrote in Italian, not Latin. He used dialogue, analogy, and narrative. He believed that truth, to be meaningful, must be shared. Today, we face a similar challenge. Science is often gated by language, by jargon, by access. Galileo's example tells us to lower those gates, not by dumbing down ideas, but by lifting up understanding. A scientist who cannot explain their work clearly is not superior, they are incomplete. Another reason Galileo matters: he knew science had social consequences. His observations did not just impact astronomy, they shook philosophy, theology, and politics. He understood that truth is rarely neutral. Sometimes, when you describe reality accurately, you threaten systems that rely on distortion. That is why he was silenced. Not for making a mistake, but for being correct too soon. Galileo teaches us that seeking truth requires courage. Courage to stand alone, if necessary. Courage to face ridicule, suppression, or worse. But also courage to admit when the data says we're wrong. Because science is not a shield for ego. It is a discipline of humility. Galileo practiced that humility. He changed his views when observations demanded it. He did not claim certainty where none existed. He left space for future thinkers to build beyond him. That is perhaps the greatest sign of a scientist, to know your work is unfinished, and to welcome that. Let's talk about the modern world. We now live in a time of immense technological capability. We can see inside atoms, simulate the birth of the universe, and modify genomes. But we also face new dangers: misinformation, polarization, pseudoscience, and anti-intellectualism. In this world, Galileo's legacy is not a chapter in a textbook, it's a toolkit. When faced with a viral claim, Galileo would ask, is this observed? Is it measured? Can others reproduce it? When confronted with a popular opinion, he would ask, does it match reality? And if not, he would challenge it. That is how science pushes forward, not by consensus, but by evidence. We honor Galileo not by agreeing with him, but by thinking like him, by refusing to let tradition silence curiosity, by asking questions no one else is willing to ask, and by demanding that our beliefs match the world, not the other way around. unwinding. The story also reminds us that progress is not always linear. There are setbacks. Galileo's discoveries were real, but his trial delayed their acceptance for generations. Just as today, truth can be sidelined for profit, for ideology, for convenience. But in the long run, reality wins. It may take years or centuries, but truth, when tested, measured, and verified, endures. And so does the memory of those who pursued it honestly. Galileo is one of those few. We also see Galileo's imprint in every scientific tool. Each microscope, each particle accelerator, each spectrometer is a descendant of his telescope. They extend our senses. They turn the invisible into data. They bring us closer to understanding the universe, but the tool is only as good as the mind behind it. And Galileo's mind was not content to observe. It wanted to understand, to see not just that something happened, but why, to model it mathematically, to link it to other phenomena, to discover patterns, causes, and systems. This is how knowledge accumulates, not through scattered facts, but through coherence. Galileo's emphasis on mathematics as the language of nature shaped generations, from Newton's equations to Maxwell's fields, from Schrödinger's wave function to Einstein's tensors. Each was built on Galileo's premise that nature is lawful and law can be expressed as number. This belief is not religious. It is methodological. It tells us where to look, how to measure, and how to recognize when we've found something real. Galileo turned the universe into a readable book and taught us how to read it. But perhaps the deepest reason Galileo still matters is this: he believed in human reason. He believed that ordinary minds could understand extraordinary truths, if given the tools. That truth is not reserved for the elite, the ordained, or the powerful. It belongs to those who observe carefully, reason honestly, and persist patiently. This democratic spirit of science is under threat in many parts of the world. Not everyone wants an informed population. Not everyone benefits from critical thinking. But Galileo reminds us that knowledge, once seen, cannot be unseen. That even under pressure, truth has a shape. It resists distortion. He may have been silenced in life, but his ideas spoke louder than his censors, and they still do. So why does Galileo matter? Because every scientific method owes him. Every equation of motion traces back to his ramps. Every planetary model builds on his observations. Every call for evidence over assertion echoes his voice. And every time someone asks, what do we actually know, and how do we know it? They are, knowingly or not, thinking in his tradition. Galileo matters because the pursuit of truth still matters. Not just for science, for society, for freedom, for the future. His life shows us what is possible when we combine curiosity with courage, precision with imagination, and skepticism with method. He reminds us that the greatest discoveries are not just about what we learn, but about how we learn to learn. Not just what we see, but how we come to see differently. Galileo looked up and saw not just stars, but a new way to think. And for that, we do not just remember him, we continue him. Thank you for listening to this series on Galileo Galilei. If it sparked a thought, a question, or a sense of wonder, then the tradition he began is alive in you too. Keep observing, keep questioning, keep learning, and most of all, stay curious.